What if I told you that the universe has a hidden language, one written not in stars or galaxies, but in invisible threads that bind particles together across unimaginable distances? This isn't science fiction. It's the strange, beautiful truth of cosmic entanglement, a phenomenon so bizarre that even Albert Einstein called it spooky action at a distance. Picture this: two particles born from the same quantum event, separated by millions of light years, yet still dancing in perfect, instantaneous harmony. Change one and the other responds faster than light, defying everything we thought we knew about time and space. How is this possible, and what does it mean for our understanding of reality itself? For decades, this enigma has haunted the brightest minds in physics, tearing at the fabric of classical science and forcing us to rewrite the rules of the cosmos. Cosmic entanglement isn't just a curiosity, it's a gateway to a deeper layer of existence, where the universe operates in ways that seem almost magical. Think about it: if particles can communicate across vast distances without any physical connection, what does that say about the nature of space? Could entanglement be the hidden architecture of reality, woven into the very foundation of everything we see and don't see? The implications are staggering, touching everything from black holes to the birth of the universe itself. Today, we're diving headfirst into this cosmic mystery, unraveling the secrets that have puzzled scientists for generations. We'll explore how entanglement challenges our most fundamental ideas about cause and effect, how it might hold the key to quantum computing, and even how it could reshape our vision of spacetime. Along the way, we'll confront questions that blur the line between science and philosophy. Is the universe fundamentally connected in ways we're only beginning to grasp? Are we, too, part of this vast, entangled web? Strap in, because by the end of this journey, you'll never look at the night sky the same way again. The cosmos is far stranger, far more interconnected than we ever dared to dream. At the heart of this cosmic mystery lies a battle of ideas, one that began not in the depths of space, but in the quiet halls of academia. In 1935, Albert Einstein, alongside physicists Boris Podolsky and Nathan Rosen, published a paper that would shake the foundations of physics. They posed a simple but devastating question. If quantum mechanics was correct, then two particles could become inextricably linked, instantly influencing each other no matter how far apart they drifted. To Einstein, this was unthinkable. The very idea violated his theory of relativity, which insisted nothing could travel faster than light. He called it spooky action at a distance, dismissing it as proof that quantum theory must be incomplete. But here's where the story twists. What Einstein intended as a critique became the very blueprint for one of nature's most profound secrets. The EPR paradox, as it came to be known, wasn't just a challenge, it was a roadmap. Scientists realized entanglement wasn't a flaw in quantum mechanics, it was a feature. Take two electrons born from the same atomic collision. Even if you separate them by the width of the galaxy, measuring one would instantly determine the state of the other. No signal passes between them, no force connects them, yet they move as if choreographed by some unseen hand. The implications were staggering. For centuries, physics had relied on locality, the idea that objects are only influenced by their immediate surroundings. Entanglement tore that assumption to shreds. It suggested the universe operates on a level where distance is an illusion, where particles share a hidden unity that transcends space and time. And while Einstein resisted, others like Niels Bohr embraced the strangeness, arguing that quantum mechanics didn't need to make intuitive sense, it just needed to describe reality accurately. This clash of titans set the stage for decades of experimentation. In the 1960s, physicist John Bell devised a way to test whether entanglement was real or just a mathematical quirk. His equations became the litmus test for quantum weirdness, and when labs finally ran the experiments in the 1980s, the results were undeniable. Particles really were communicating faster than light, not through any force we could detect, but through a deeper, more mysterious connection. The universe, it seemed, was playing by rules far stranger than Einstein could have imagined. What began as a theoretical debate had blossomed into a revolution. Today, entanglement isn't just a curiosity. It's the cornerstone of cutting-edge technologies like quantum computing and ultra-secure cryptography. But perhaps its greatest gift is the way it forces us to rethink reality itself. If particles can defy the limits of space, what else might be possible? Are we glimpsing a deeper layer of existence, one where separateness is an illusion, and everything is woven together in a cosmic dance we're only beginning to understand? The answers, much like entangled particles, remain tantalizingly just out of reach. Einstein's resistance to entanglement wasn't just stubbornness, it was the collision of two worldviews. On one side stood Einstein, the architect of relativity, who believed the universe operated on strict, deterministic laws. For him, particles influencing each other instantaneously across vast distances wasn't just counterintuitive, it threatened the very order he'd spent his life unraveling. God does not play dice, he famously declared, rejecting the randomness at the heart of quantum theory. But on the other side stood Niels Bohr, the father of quantum mechanics, who embraced the chaos. Where Einstein saw spookiness, Bohr saw beauty, a universe fundamentally probabilistic, where particles exist in a haze of possibilities until observed. Their debates weren't just academic squabbles, they were a clash of philosophies. Picture Bohr's Copenhagen interpretation, where reality doesn't solidify until measured, against Einstein's steadfast belief in an objective cosmos ticking along like clockwork. The irony, Einstein's own work had helped birth quantum mechanics, yet he spent decades trying to reconcile it with his vision of a predictable universe. He proposed hidden variables, invisible mechanisms that might explain entanglement without defying relativity. But Bohr countered with a radical idea: there were no hidden layers. The universe at its core was simply that strange. This tension reached its peak in a series of thought experiments, each more ingenious than the last. Einstein would devise scenarios to trap quantum theory in contradictions, and Bohr, often after sleepless nights, would find elegant escapes. One famous exchange revolved around a photon's path. Einstein argued that measuring one particle's momentum shouldn't instantly determine another's position light years away. Bohr's reply: these properties aren't inherent, they're defined by the act of measurement itself. It was as if reality was a conversation, not a fixed script. Yet for all his skepticism, Einstein's pushback became quantum physics' greatest stress test. His challenges forced Bohr and others to sharpen their theories, revealing just how robust and bizarre the quantum world truly was. When John Bell later proved that no hidden variables could explain entanglement, it wasn't a defeat for Einstein's intellect but a testament to it. His resistance had illuminated the boundaries of classical physics, showing where the old rules fractured and new ones emerged. Today, we live in the universe Bohr championed, one where particles teleport information, where cats can be simultaneously dead and alive, and where entanglement underpins technologies like quantum encryption. But Einstein's questions still echo. Was he wrong, or was he glimpsing a deeper truth we haven't yet uncovered? Some physicists now speculate that spacetime itself might emerge from a vast, entangled quantum network, a cosmic tapestry where spooky action isn't the exception but the rule. In that light, perhaps both men were right. Bohr about the quantum weirdness before our eyes, and Einstein about the order waiting to be found beyond it. By the 1960s, the debate over entanglement had reached a stalemate. Einstein's camp clung to hidden variables, invisible, classical mechanisms that might explain the eerie connection between particles without breaking the speed of light. Bohr's supporters insisted quantum mechanics was complete, spookiness and all. But how could science settle a philosophical clash that played out in thought experiments and interpretations? Enter John Bell, a soft-spoken physicist from Northern Ireland who dared to ask, could entanglement be tested, not just debated? Bell's insight was as elegant as it was revolutionary. He realized that if hidden variables governed entanglement, then certain statistical relationships between particles, now called Bell inequalities, would always hold true. But if quantum mechanics was correct, these inequalities would be violated. It was a mathematical litmus test, cutting through decades of abstract argument with cold, hard numbers. The beauty of Bell's theorem lay in its simplicity. Measure enough entangled particles, and the universe itself would declare a winner. For years, the technology to run these experiments didn't exist. But by the 1980s, physicists like Elaine Aspect had refined techniques to trap and measure pairs of photons with exquisite precision. The results sent shockwaves through the scientific community. Time and again, Bell's inequalities were shattered. Particles defied the limits of hidden variables, coordinating their states in ways that classical physics couldn't explain. The kicker, the correlations between them didn't just exceed classical predictions, they matched quantum mechanics perfectly. Entanglement wasn't a quirk. It was a fundamental feature of reality. What made these findings so unsettling was how they upended our intuition about cause and effect. Imagine tossing two coins light years apart, only for both to always land on the same face instantly, without any signal passing between them. Bell's theorem proved this wasn't just a metaphor, it was how the universe worked at its deepest level. The experiments ruled out any theory where particles decide their states in advance, like two conspirators whispering before parting ways. Instead, the outcomes seemed to emerge from a shared reality that transcended space and time. Today, Bell's legacy extends far beyond settling an old debate. His theorem laid the groundwork for quantum technologies that once seemed like fantasy. Quantum cryptography, for instance, relies on entanglement to create unbreakable codes. Any eavesdropper would disrupt the delicate quantum link, alerting the sender instantly. And in quantum computing, entangled qubits perform calculations at speeds impossible for classical machines. But perhaps the most profound implication is philosophical. Bell showed us that the universe isn't just stranger than we imagined, but stranger than we could imagine. The irony, in trying to rescue Einstein's dream of a deterministic cosmos, Bell's theorem ended up confirming Bohr's vision of a quantum world brimming with inherent uncertainty. Yet even now, physicists grapple with what it all means. Some speculate that spacetime itself emerges from a vast web of entangled quantum states, a cosmic fabric woven from threads of spooky action. Others wonder if we're glimpsing a deeper layer of physics, one where the rules we take for granted are just shadows on the wall of a far stranger reality. One thing's certain, thanks to Bell, we know the quantum world doesn't play by classical rules, and that's just the beginning of the mystery. For decades, entanglement lived only on chalkboards and in thought experiments, a ghostly prediction of quantum theory that seemed too strange to be real. But in the late 20th century, physicists like Elaine Aspect brought this quantum phantom into the light of the laboratory, transforming philosophical debate into hard, measurable fact. Aspect's experiments in the 1980s didn't just confirm entanglement, they shattered our classical intuitions about how the universe works. Picture a lab where pairs of photons are born entangled, then sent racing in opposite directions toward detectors several meters apart. By the time they arrive, their polarizations, the orientation of their light waves, should be independent, like two coins flipped separately. But when Aspect's team measured them, the results sent shockwaves through physics. Every time one photon was found polarized vertically, its partner, no matter how far away, instantly aligned horizontally. No signal passed between them. No force connected them, yet their states were perfectly correlated, as if space and distance were mere illusions. The genius of these experiments lay in their precision. Aspect's team used rapidly switching detectors to rule out any hidden communication between the particles. Even if some unknown signal could travel between them, it would have needed to move faster than light, something Einstein's relativity strictly forbids. Yet the photons behaved as if they were still a single, unified system, defying the very notion of locality. It was as if the universe had a secret ledger, updating entries simultaneously across vast distances without any middleman. But the implications run deeper than laboratory curiosities. Imagine a pair of entangled particles separated by the width of the galaxy. If you measure one here on Earth, its partner instantly, without delay, snaps into a corresponding state, even if that means rewriting its properties billions of light years away. This isn't just faster than light communication. It's a complete bypass of spacetime as we know it. Some physicists speculate that entanglement reveals a deeper layer of reality, where what we perceive as separate particles are actually facets of a single, interconnected quantum entity. Today, labs routinely entangle particles across ever greater distances. In 2017, Chinese scientists sent entangled photons from a satellite to ground stations over 700 miles apart, a feat that would have seemed like magic just decades earlier. These experiments aren't just academic exercises, they're laying the groundwork for technologies like quantum networks, where information teleports securely across the globe, unhackable by conventional means. Yet for all our progress, the central mystery remains: how does nature pull off this cosmic synchronization? Is entanglement a glitch in our understanding, or a clue pointing toward a grander theory, one where spacetime itself emerges from a web of quantum connections? Every experiment tightens the grip of quantum reality, leaving us to wonder, if particles can defy the limits of distance, what other impossibilities might the universe be hiding? If you think quantum teleportation belongs solely in the realm of sci-fi, prepare to have your mind stretched. This isn't about dematerializing humans a la Star Trek, it's something far more profound. Scientists have already harnessed entanglement to teleport quantum information across labs, cities, and even between Earth and space. Here's how it works. Imagine two entangled particles, like photons, acting as cosmic twins. When you manipulate the state of one, its partner instantly mirrors that change, no matter how far apart they are. This isn't just a parlor trick. It's the backbone of a radical new way to transmit data. The process starts with what physicists call a Bell measurement. Let's say Alice wants to teleport the quantum state of a particle to Bob. She entangles one photon with a second, then sends the second to Bob while keeping the first. When Alice measures her photon and its entangled partner, the act of measurement itself collapses their states, but here's the magic. Bob's photon, now miles away, instantly assumes the exact state of Alice's original particle, as if the information leaped across space without traveling through it. No wires, no signals, just pure quantum weirdness. In 2017, Chinese scientists made history by teleporting a photon's quantum state from Earth to a satellite orbiting over 300 miles overhead. The photon didn't physically move, its information did, riding the invisible thread of entanglement. This breakthrough wasn't just a milestone, it was a glimpse into a future where quantum networks could span the globe, enabling unhackable communication. Imagine sending encrypted data with perfect security, where any attempt to intercept it would immediately disrupt the entanglement, alerting both sender and receiver. But the implications go beyond secure messaging. Quantum teleportation could turbocharge computing. Traditional computers process bits as zeros or ones, but quantum qubits can be both thanks to superposition. Teleporting qubits between processors could link quantum computers into a single planet-sized brain, solving problems like climate modeling or drug discovery in minutes instead of millennia. Yet for all its promise, teleportation remains shrouded in mystery. How exactly does information bypass spacetime? Some theories suggest entanglement reveals a hidden layer of reality where distance is an illusion, and particles are just nodes in a vast quantum network. Others wonder if we're seeing hints of a deeper physics, one where the universe operates not as separate objects, but as a unified, entangled whole. The line between science fiction and science fact has never been blurrier. While we won't be teleporting humans anytime soon, the ability to move quantum information instantly is already reshaping our technological horizon. And who knows? If entanglement truly binds the universe together, perhaps the stars themselves are closer than they appear. If entanglement seems to defy the rules of space and time, what does that say about the very nature of reality itself? Some of the boldest theories in physics now suggest that spacetime, the stage on which the universe plays out, might not be fundamental at all. Instead, it could emerge from something far stranger, a vast, tangled web of quantum connections, where entanglement isn't just a phenomenon but the very fabric of existence. Take the holographic principle, for instance. It proposes that all the information in our three-dimensional universe might actually be encoded on a two-dimensional surface at its boundary, like a cosmic projector screen. In this view, the world we experience is akin to a hologram, a richly detailed illusion emerging from deeper, entangled quantum bits. Imagine scribbling a message on a sheet of paper, then crumpling it into a ball. From the outside, the words seem lost, but every bit of information is still there, just folded into a new form. The holographic universe works similarly, with entanglement acting as the invisible glue that binds the lower dimensional code to our higher dimensional reality. Then there's the ER equals EPR conjecture, a radical idea that bridges entanglement and wormholes. In 1935, Einstein and Rosen proposed the existence of bridges through spacetime, later dubbed Einstein-Rosen bridges or wormholes. That same year, Einstein, Podolsky, and Rosen highlighted the paradox of entanglement. For decades, these concepts seemed unrelated. But in 2013, physicists Leonard Susskind and Juan Maldacena suggested they might be two faces of the same coin. Their theory posits that entangled particles could be connected by microscopic wormholes, threading through higher dimensions we can't perceive. In other words, what looks like spooky action at a distance might actually be particles linked by hidden tunnels in the fabric of reality. This isn't just wild speculation. The math behind these ideas is rigorous, and they offer tantalizing solutions to long-standing puzzles. Black holes, for example, appear to destroy information, violating quantum mechanics. But if spacetime is built from entanglement, information might not vanish. It could simply be scrambled into a form we don't yet understand. Similarly, the Big Bang might not have been a singular explosion in empty space, but the crystallization of a quantum network into the dimensions we recognize today. The implications are staggering. If entanglement underpins spacetime itself, then the universe isn't just interconnected, it's fundamentally inseparable. Particles aren't distant actors communicating mysteriously. They're nodes in a cosmic net, their links woven into the architecture of reality. This perspective transforms how we see everything from gravity to the birth of galaxies. It even hints that our perception of time might be a side effect of quantum correlations stretching and evolving across the cosmos. Yet for all its elegance, this vision raises profound questions. If space-time is emergent, what lies beneath it? Could there be a deeper, non-geometric layer of reality where quantum threads intertwine without reference to distance or direction? And if entanglement is so fundamental, why do we experience a world of seemingly separate objects? Some theorists speculate that decoherence, the process by which quantum systems interact with their environment, creates the illusion of individuality, like ripples on a pond obscuring the water's true unity. We're left with a universe far stranger than Newton or even Einstein imagined. The old metaphor of the cosmos as a clockwork mechanism gives way to something more akin to a living neural network pulsing with quantum connections. Whether through holography, wormholes, or some yet undiscovered framework, one thing is clear: entanglement isn't just a quirk of tiny particles. It might be the loom on which reality is woven, thread by invisible thread. And as we pull at these threads, we're not just exploring the universe, we're unraveling the very definition of what it means to exist. Black holes have long been the universe's ultimate enigmas, cosmic traps where gravity crushes matter into oblivion and even light can't escape. But what if these celestial monsters aren't just destroyers? What if they're also keepers of quantum secrets, hiding answers to the puzzle of entanglement in their inky depths? At first glance, the two seem unrelated. Entanglement deals with particles whispering across space, while black holes warp spacetime itself. Yet when Stephen Hawking discovered that black holes slowly evaporate, radiating away their mass, he stumbled into a paradox that would tie these ideas together in the most unexpected way. Hawking's calculations showed that black holes emit radiation later named Hawking radiation, as quantum fluctuations near their event horizons cause particles to escape. But here's the catch: this radiation appeared random, carrying no information about the matter the black hole had swallowed. That posed a problem. Quantum mechanics insists information can never be truly lost. If a book burns, its ashes might seem chaotic, but in principle, every word could be reconstructed from the smoke and debris. Hawking's radiation, though, seemed to erase information permanently, violating quantum law. This contradiction became known as the black hole information paradox, and it set off a decades-long battle between gravity and quantum theory. Enter entanglement. In the 1990s, physicist Leonard Susskind proposed a radical solution. What if the particles escaping as Hawking radiation weren't random at all? What if they were subtly entangled with particles already inside the black hole? Imagine a pair of entangled photons at the event horizon. One falls in, the other escapes. Though they're separated, their quantum link remains. Over time, as more particles escape, the radiation outside becomes a tangled web of connections to the black hole's interior. In this view, information isn't lost, it's scrambled, like a message written in invisible ink, waiting for the right key to reveal it. This idea blossomed into the concept of black hole complementarity, which suggests that from an outsider's perspective, information never actually enters the black hole. It's smeared across its surface, encoded in the Hawking radiation. Meanwhile, from the perspective of someone foolish enough to dive in, the information seems to pass through the horizon unharmed. Both viewpoints can't be true simultaneously, yet quantum mechanics allows for such paradoxical truths. It's as if the universe has two sets of books, each telling a different but equally valid story. The plot thickened when researchers realized entanglement might play an even deeper role. In 2013, physicists discovered that the math describing entanglement entropy, a measure of quantum connections, mysteriously mirrors the equations governing black hole thermodynamics. It was as if the event horizon itself were a vast network of entangled threads, stitching together the fabric of spacetime. Some theorists now speculate that black holes are cosmic knots of quantum information, where entanglement doesn't just preserve data, it shapes the very geometry of reality. This interplay between black holes and entanglement has birthed wild new ideas, like the holographic principle, which suggests our three-dimensional universe could be a projection of quantum data stored on a two-dimensional surface. Think of it like a movie screen. The images appear lifelike, but they're really just patterns of light on a flat canvas. Similarly, the cosmos might be a hologram, with entanglement acting as the pixels that construct our illusion of depth and distance. The implications are staggering. If black holes and entanglement are two sides of the same coin, then solving their mysteries could unlock a theory of quantum gravity, a unified framework that reconciles the cosmic and the quantum. It might explain how spacetime emerges from something more fundamental, or even reveal whether our universe is just one thread in a vast, entangled multiverse. For now, the answers remain hidden behind event horizons, but the journey to find them is reshaping our understanding of existence itself. One thing's certain: in the quantum dance of black holes, nothing is ever truly lost, only transformed. Imagine the universe as a vast cosmic cinema, where the three-dimensional world we experience is nothing more than a dazzling projection from a flat, two-dimensional screen at the edge of reality. This isn't a metaphor, it's the essence of the holographic principle, a theory so revolutionary it redefines our understanding of existence itself. At its core, this idea suggests that all the information in our universe, every star, every atom, even your thoughts right now, might be encoded on a distant, two-dimensional boundary, like data etched onto the surface of an unimaginably vast cosmic hard drive. And the key to this mind-bending possibility, entanglement, the same quantum phenomenon that links particles across space and time. Think of it like this: when you watch a hologram, a flat surface creates the illusion of depth, tricking your brain into seeing three dimensions where only two exist. The holographic principle proposes that reality itself operates similarly. The three-dimensional cosmos we perceive could be a kind of illusion, emerging from a network of entangled quantum bits on some far-off boundary. It's as if the universe is a tapestry woven from countless threads of quantum connections, with entanglement stitching together the very fabric of space and time. But how does this actually work? Enter the work of physicist Juan Maldacena, who in 1997 discovered a startling mathematical link between string theory and quantum gravity. His equations showed that a theoretical universe with 5 dimensions, a playground for string theorists, could be perfectly described by a 4-dimensional quantum field theory on its boundary. The implications were profound. The laws of physics in higher dimensions might emerge from simpler, lower-dimensional rules, and at the heart of this correspondence was entanglement, acting as the bridge between the two descriptions. Without it, the holographic universe would collapse like a house of cards. This isn't just abstract theorizing. In 2014, experiments with ultra-cold quantum systems provided tantalizing hints that the holographic principle might reflect reality. Researchers found that the entanglement entropy, a measure of quantum connections, in certain materials followed mathematical patterns eerily similar to those predicted by holographic models. It's as if nature itself were whispering that the universe operates like a cosmic projection, with entanglement serving as the hidden pixels that construct our experience of depth, distance, and even time. The philosophical implications are staggering. If the holographic principle holds, then the solid, tangible world around us is akin to a shadow on a cave wall, a mere echo of a deeper, more fundamental reality. Objects we perceive as separate might be threads in a vast quantum tapestry, their individuality an illusion born from our limited perspective. Even more unsettling, if entanglement binds the universe's underlying code, then what we call space might not be fundamental at all, but a byproduct of quantum correlations stretching across the cosmic horizon. Yet for all its elegance, the holographic principle raises as many questions as it answers. Where exactly is this two-dimensional boundary? Is it the edge of the observable universe or something stranger? And if we're just projections, what or who is doing the projecting? Some theorists speculate that black holes might hold clues, with their event horizons acting as natural holographic screens. Others wonder if the principle hints at a multiverse, where each universe is a separate projection from some unfathomable quantum source. One thing's certain: if the holographic principle is correct, then entanglement isn't just a curious feature of the quantum world, it's the very language of reality, the ink with which the cosmos writes itself into existence. And that means the mysteries we've been exploring, spooky action, quantum teleportation, even black holes, aren't isolated puzzles. They're pieces of a grander picture, one where the universe is far more interconnected, far more alien, and far more holographic than we ever dared to dream. Einstein's general relativity paints the cosmos in broad, elegant strokes, a dynamic stage where matter tells spacetime how to curve, and spacetime tells matter how to move. It predicts black holes bending light and the expansion of the universe with breathtaking precision. Yet zoom into the quantum realm and the rules crumble. Here, particles flicker in and out of existence, occupy multiple states at once, and whisper to each other across galaxies through entanglement. These two frameworks, relativity's cosmic choreography and quantum mechanics' subatomic chaos, should converge when gravity meets the quantum world. But when physicists try to merge them, the math explodes into infinities, as if the universe itself is refusing to reconcile its own laws. This isn't just a technical hiccup, it's a crisis at the heart of physics. For decades, theorists have chased a theory of quantum gravity, a Rosetta Stone that could translate between these seemingly incompatible languages, and increasingly, they suspect entanglement might hold the missing cipher. Take loop quantum gravity, one leading approach. It proposes that spacetime isn't smooth and continuous but woven from microscopic loops, like a fabric spun from trillionth of a trillionth scale threads. These loops don't just exist in space, they're entangled, they're quantum links generating the very geometry we experience as distance and time. In this view, gravity isn't a force propagating through space, it's the emergent tremor of this quantum network rearranging itself. String theory, another contender, takes a different but equally entanglement-rich path. It imagines particles as vibrating strings, with their harmonies dictating mass, charge, and other properties. But to make the math work, these strings must dance through 10 or 11 dimensions, most curled up too small to detect. How do these hidden dimensions stay compactified? Entanglement again. The theory suggests these extra dimensions are stabilized by quantum links, like invisible guy wires holding the structure of reality taut. Some versions even propose that spacetime itself is a hologram projected from entangled strings on a distant boundary, blurring the line between where the universe is and how it's encoded. The most tantalizing clues come from black holes' nature's own quantum gravity labs. When matter falls into a black hole, classical physics says it's gone forever. But quantum mechanics insists the information it carried must persist, likely in the Hawking radiation leaking from the event horizon, the only way both can be true. If the interior and exterior of the black hole are entangled, with the radiation acting as a scrambled quantum mirror of what fell in, this realization led to the ER=EPR conjecture, the idea that entangled particles EPR might be connected by microscopic wormholes threading through higher dimensions like subway tunnels beneath the city of spacetime. If this seems abstract, consider a humble magnet. To a child, its attraction feels like magic, but we know it emerges from countless aligned electron spins. Similarly, gravity might be the collective effect of spacetime's underlying quantum entanglements. Experiments are already testing these ideas. In 2020, physicists used quantum computers to simulate how entanglement entropy, a measure of quantum connections, mimics the equations of emergent spacetime. The results hinted that our familiar four-dimensional world could indeed arise from a lower-dimensional quantum substrate, like a three-dimensional shadow cast by a two-dimensional flame. Yet challenges remain. Quantum gravity theories often lack experimental predictions, leaving scientists to wrestle with mathematical elegance as their guide. Some argue we're missing a deeper principle, like relativity's equivalence principle or quantum mechanics uncertainty, a rule so fundamental it reshapes how we see both frameworks. Others suspect entanglement alone isn't enough. Perhaps it's part of a larger tapestry involving new physics, like supersymmetry or extra dimensions. What's clear is that entanglement has shifted from a quantum curiosity to a potential architect of reality. It's as if we've spent centuries studying the ripples on a pond, only to realize the water itself is made of something stranger and more profound. Whether through loops, strings, or some yet undiscovered structure, the path to quantum gravity seems to wind through a landscape where here and there, before and after, are illusions, and entanglement is the thread stitching them into the world we know. Time's arrow has always flown in one direction from past to future, like an unbreakable cosmic rule. But why? Why do eggs shatter but never unshatter? Why do memories cling to the past but never the future? Classical physics shrugs. It treats time as a stage, indifferent to the play unfolding upon it. Yet quantum mechanics, with its eerie entanglement, might finally crack this ancient mystery wide open. The key lies not in the ticking of clocks, but in the hidden quantum connections that weave the fabric of reality itself. Picture a deck of cards fresh from the box, neatly ordered, pristine. Shuffle it, and chaos takes over. The transition from order to disorder defines what physicists call entropy, the universe's tendency toward messiness. But here's the twist. At the quantum level, entropy isn't just about disorder. It's about entanglement. Every time particles interact, they entangle, spreading their quantum information like ink in water. This entanglement entropy grows relentlessly, mirroring the arrow of time we experience. The universe might not have a preference for past or future. It might simply be unraveling quantum correlations, and time is the byproduct. Consider a cup of coffee cooling in a room. Classically, we'd say heat flows from hot to cold because entropy increases. But quantum mechanics offers a deeper explanation. The coffee's molecules entangle with the air, their quantum states spreading outward in an irreversible tide. The more entangled the system becomes, the harder it is to rewind the process. In this view, time's forward march isn't a fundamental law. It's the echo of quantum correlations proliferating across the cosmos. The implications are dizzying. If entanglement entropy drives time, then the Big Bang wasn't just the birth of space and matter. It was the moment quantum connections began their exponential spread. The early universe was a sea of particles in perfect sync, a low entropy state primed to unravel. As entanglement grew, so did time's arrow, carrying us from cosmic dawn to the present. Some theorists even speculate that black holes, the ultimate entropy factories, might be time's accelerators, their voracious appetites for entanglement entropy fueling the universe's clock. But what if we could reverse it? In theory, a system with decreasing entanglement entropy would experience time running backward. While that's impossible for something as complex as a coffee cup, labs have already created tiny quantum systems where entropy temporarily dips, creating localized time reversals. These experiments don't violate thermodynamics, they highlight how deeply time's flow is tied to quantum mechanics. The most radical idea, time might not exist as a fundamental dimension at all. Instead, it could emerge from the universe's quantum network, a shadow cast by entanglement's ceaseless dance. Just as space might be a hologram, time could be an illusion, a collective hallucination born from particles whispering to one another across the void. Einstein once called time a stubbornly persistent illusion. He might have been closer to the truth than he knew. As we peer deeper into this quantum labyrinth, one thing becomes clear: the arrow of time isn't just a feature of the universe. It might be the universe, a story written in the language of entanglement, where every moment is a stitch in the fabric of reality itself. And if that's true, then the past, present, and future aren't just points on a line. They're threads in a tapestry still being woven. There's a moment in every quantum experiment that feels like magic, the instant a particle's fuzzy cloud of possibilities snaps into a single, definite state. This is the measurement problem, the stubborn enigma at the heart of quantum mechanics. Why does observation force a particle to choose between being here or there, spinning up or down? And stranger still, how does entanglement, the invisible thread linking particles across the universe, play into this cosmic game of peek-a-boo? Consider Schrödinger's infamous cat trapped in a box where it's both alive and dead until someone looks. The thought experiment wasn't just a critique of quantum weirdness, it exposed a paradox. If particles exist in superpositions, multiple states at once, why does measuring them destroy that delicate balance? One explanation, the Copenhagen interpretation, suggests the act of observation itself collapses the wave function, like a camera flash freezing a hummingbird's wings mid-flight. But this raises thorny questions. What counts as a measurement? Is it a human eye, a detector? And if entangled particles are involved, does measuring one instantly collapse its partner's state too, even if they're light years apart? This isn't just philosophical hand-wringing. Lab experiments with entangled photons show that measuring one does indeed determine its twin's properties instantaneously, with no signal passing between them. It's as if the universe updates its ledger faster than light, violating Einstein's cosmic speed limit. Some physicists, like Hugh Everett, proposed a way out, the many worlds interpretation. In this view, the wave function never collapses. Instead, every possible outcome plays out in branching realities. Measure an electron and the universe splits, one where it spun up, another where it spun down. Entanglement, then, becomes a thread weaving these parallel worlds together, linking alternate versions of particles across the multiverse. Yet another camp argues the problem lies in our definition of observation. Modern interpretations like quantum decoherence suggest superpositions aren't destroyed by conscious observers, but by interaction with the environment. Imagine a drop of ink in water. At first, it's distinct, but soon it spreads and blurs until the water is uniformly tinted. Similarly, a particle's quantum states leak into their surroundings, making superposition impossible to maintain. Entanglement accelerates this process. When two particles are linked, decoherence ripples through both, locking them into correlated states even if no one's watching. The implications ripple far beyond labs and equations. If measurement shapes reality, does consciousness play a role in constructing the universe? Some theorists, like John von Neumann, speculated that the observer's mind might be the ultimate collapse mechanism. an idea that edges into metaphysics. Others, like Roger Penrose, propose gravity as the culprit, with spacetime itself acting as the threshold where quantum possibilities crystallize into classical facts. What makes the measurement problem so vexing is that it's not just about physics, it's about the nature of reality. Are we uncovering fundamental truths, or are those truths changing because we're looking? Entanglement adds layers to this mystery, suggesting that here and there might be illusions, and that the universe's building blocks are bound by connections deeper than distance or time. As we peer deeper into the quantum realm, one thing becomes clear: the act of looking doesn't just reveal reality, it might just create it. What if every choice you've ever made, every path taken or not taken, exists simultaneously in a web of alternate realities? This isn't just the stuff of sci-fi. It's the spine-tingling premise of the many worlds interpretation, a radical theory proposing that the universe doesn't settle on a single outcome when quantum measurements occur. Instead, it branches endlessly, spawning parallel realities where every possible version of events plays out. And here's where entanglement enters the picture. Those spooky quantum links might not just connect particles across space, they could be stitching together entire universes in an unfathomably vast multiverse. Think of Schrödinger's cat again. In the Copenhagen interpretation, opening the box collapses the cat into either alive or dead. But many worlds says there's no collapse, just a split. In one universe, you find a purring cat, in another, silence. Both outcomes are real, each existing in its own timeline. Now imagine this happening not just in thought experiments, but trillions of times per second, with every quantum event, every electron spin, every photon's path spawning new branches. The result, a cosmic tree with infinite limbs, each a self-contained reality. Entanglement could be the glue holding this multiverse together. Picture two particles linked across galaxies. When you measure one, the many worlds interpretation says the universe splits. One branch where the particle spins up, another where it spins down. But here's the twist: those particles remain entangled across branches. In essence, the quantum thread doesn't just span space. It weaves through alternate realities, tying them together in a way that defies classical intuition. Some theorists even suggest that these cross-world entanglements could explain quantum probabilities. The randomness we observe might just be our limited view of a multiverse where every outcome happens somewhere. Critics argue this is untestable metaphysics, but proponents point to eerie consistencies in quantum math. The equations don't naturally describe wave function collapse, they describe endless branching. And if entanglement connects worlds, it might solve puzzles like quantum interference, where particles seem to sense multiple paths at once. Perhaps they're not sensing, they're sampling other branches of reality. The implications are staggering. If many worlds is correct, there's a version of you who became an astronaut, another who invented time travel, and countless more in realities beyond imagination. But this isn't just about cosmic spectacle. It reshapes how we see existence itself. Reality isn't a single thread. It's a tapestry of every possible what if, with entanglement as the loom. And that raises a haunting question. In a multiverse this vast, what does it even mean to be you? Imagine a world where your coffee cup could be simultaneously on your desk and in the kitchen, until you glance at it, forcing it to choose a location. That's the bizarre reality quantum particles inhabit, existing in multiple states at once. Yet we never see cats both alive and dead, or cars parked in two spaces simultaneously. Why doesn't quantum weirdness scale up to our everyday experience? The answer lies in a phenomenon called decoherence, the universe's subtle way of hiding quantum magic in plain sight. Decoherence begins with entanglement's relentless reach. When a quantum particle interacts with its environment, whether a stray photon, a dust mote, or even the air itself, it doesn't just bump into these objects, it entangles with them. Picture a drop of ink falling into a glass of water. At first, the ink remains distinct, swirling in delicate patterns, but soon it spreads, blending until the water is uniformly tinted. Decoherence works similarly. A particle's pristine quantum state, with all its simultaneous possibilities, becomes hopelessly tangled with countless particles in its surroundings. The result, those delicate superpositions leak into the environment, becoming so scrambled that they're effectively lost to observation. This isn't just theoretical. Lab experiments with tiny objects like buckeball soccer ball shaped molecules of carbon show that quantum behavior persists until interactions with the environment overwhelm it. Cool these molecules to near absolute zero, shielding them from disruptive forces, and they'll behave like waves passing through multiple slits at once. But warm them to room temperature, and they act like classical particles, their quantum nature drowned out by thermal noise. The larger an object, the more particles it contains, and the faster decoherence smothers its quantum quirks. A single electron can maintain superposition for microseconds or longer, while a grain of sand decoheres almost instantaneously. The implications are profound. Decoherence doesn't just explain why we don't see quantum strangeness in daily life. It bridges the chasm between the quantum and classical worlds. Some physicists compare it to a magician's sleight of hand. The universe isn't erasing quantum effects. It's hiding them in plain sight by spreading their information across countless entangled particles. This perspective transforms the measurement problem. Instead of a conscious observer collapsing the wave function, decoherence suggests the environment acts as a continuous, unconscious observer, relentlessly nudging quantum systems toward classical behavior. Yet mysteries remain. Why does decoherence produce the specific classical outcomes we observe? And could we ever reverse it, coaxing a coffee cup back into superposition? Some theorists speculate that exotic environments like the vacuum of space or the frigid interiors of neutron stars might harbor macroscopic quantum states. Others wonder if life itself exploits delicate balances between coherence and decoherence, with processes like photosynthesis potentially relying on quantum effects. One thing's certain, decoherence reveals a universe far more interconnected than we ever imagined. Every particle is in constant dialogue with its surroundings, its quantum whispers amplified or silenced by the cosmic chorus of entanglement. What we perceive as solid, predictable reality might just be the tip of a quantum iceberg, an emergent simplicity bobbing atop unfathomable depths of quantum complexity. Could life itself be entangled? At first glance, the warm, messy world of biology seems light, years away from the frigid precision of quantum physics. Yet mounting evidence suggests nature might have been exploiting quantum tricks long before humans even dreamed of them. Take photosynthesis, that miraculous process plants use to turn sunlight into energy. When sunlight hits a leaf, its energy needs to find the reaction center where it can be stored. Classically, this should be slow and inefficient, like a blindfolded hiker stumbling through a forest, but plants achieve near-perfect efficiency. How? Some scientists believe the answer lies in quantum coherence, the same fragile state that allows particles to exist in multiple places at once. Experiments on green sulfur bacteria reveal something astonishing. The energy from absorbed light doesn't hop randomly between molecules. Instead, it spreads out like a wave, exploring multiple pathways simultaneously through quantum superposition. This lets it test all possible routes to the reaction center at once, funneling energy with uncanny precision. Even more striking, these quantum effects persist at room temperature, defying expectations that such delicate states would instantly collapse in warm, wet biological systems. Could entanglement be the secret ingredient, linking molecules across the photosynthetic machinery like an invisible quantum Wi-Fi network? Then there's the mystery of bird migration. Every year, European robins navigate thousands of miles with pinpoint accuracy, sensing Earth's magnetic field in ways that baffle scientists, the leading theory. A protein called cryptochrome in their eyes might host entangled electron pairs. When these electrons interact with Earth's magnetic field, their quantum states could shift, creating a biochemical compass sensitive enough to guide a bird across continents. Lab studies show synthetic cryptochrome molecules do exhibit quantum-sensitive reactions, hinting that evolution may have stumbled upon quantum entanglement as a survival tool. But the most controversial frontier lies in the human brain. Some theorists, like physicist Roger Penrose, propose that microtubules, tiny protein structures in neurons, could harbor quantum states. In this view, consciousness itself might emerge from orchestrated quantum collapses in these microtubules, weaving our thoughts from the fabric of quantum possibility. Critics argue the brain is too warm and noisy for such delicate effects, yet intriguing parallels exist. Anesthetics, which selectively shut off consciousness, seem to disrupt quantum coherence in microtubules, while psychedelics enhance it, a correlation that's hard to dismiss as coincidence. The debate rages on. Skeptics point out that quantum effects in biology are fleeting and hard to verify. But if even a fraction of these claims hold, the implications are staggering. Life might not just exist in the universe, it could be tapping into its deepest quantum secrets, harnessing entanglement to see, grow, and think in ways we're only beginning to decode. Whether these quantum whispers are central to biology or mere cosmic background noise, one thing's clear: the line between the quantum and the living is far blurrier than we ever imagined. Inside a quantum computer, the ordinary rules of logic dissolve. Where classical computers rely on bits, simple switches flipped to 0 or 1, quantum machines wield qubits, particles that can be 0, 1, or both simultaneously thanks to superposition. But the real magic happens when these qubits entangle, linking their fates across the machine. Picture two coins spinning in perfect sync. Flip one, and the other instantly lands the same way, no matter how far apart they are. Now scale that to thousands of qubits, all whispering to each other through quantum threads, and you've got a processor that doesn't just calculate, it explores infinite possibilities at once. This isn't just theoretical. In 2019, Google's Sycamore processor solved a problem in 200 seconds that would take the world's fastest supercomputer 10,000 years. The task: generating random numbers, a mundane test but one that proved quantum computers could outperform classical ones at specific workloads, the secret sauce. Entanglement. By choreographing qubits into intricately linked networks, Sycamore navigated computational paths no classical machine could map. The implications are staggering. Take cryptography. Modern encryption relies on the fact that factoring huge numbers takes classical computers centuries. But a quantum machine with enough entangled qubits could crack these codes in hours, rewriting the rules of digital security. Pharmaceutical companies are salivating too. Simulating complex molecules key to designing new drugs requires tracking every possible interaction between atoms, a task so computationally intense that classical machines often fail. Entangled qubits, though, can model these interactions natively, mirroring the quantum behavior of electrons and protons. Imagine designing a cancer drug by testing millions of molecular configurations in seconds, not decades. Yet for all their potential, quantum computers remain temperamental beasts. Entanglement is fragile. A single stray photon or temperature fluctuation can destroy it in nanoseconds. Engineers combat this by cooling chips to near absolute zero and shielding them in vacuum chambers. Even then, errors creep in. That's why today's quantum machines rely on error-correcting codes that consume most of their qubits just to keep the remaining few stable. It's like building a cathedral where 90% of the stones are scaffolding. Beyond these technical hurdles lies a deeper philosophical puzzle. If entanglement allows quantum computers to explore countless realities simultaneously, does that mean they're tapping into parallel universes? Some interpretations of quantum mechanics suggest exactly that, with each qubit superposition representing a branch in the multiverse. Others argue the machines simply exploit mathematical shortcuts within our own reality. Either way, one thing's clear: entanglement isn't just a tool for computation. It's a window into the universe's most profound mysteries, revealing a cosmos far more interconnected and far stranger than we ever imagined. Picture sending a message so secure that any attempt to intercept it would instantly alert both sender and receiver, not through clever software, but through the fundamental laws of physics. This isn't the plot of a spy thriller. It's the promise of quantum cryptography, where the spooky link between entangled particles becomes the ultimate guardian of secrets. At its core lies quantum key distribution, or QKD, a method so robust it doesn't just resist hacking, it exposes hackers the moment they take a peek. Here's how it works. Imagine Alice and Bob want to share a private message. Instead of relying on complex mathematical codes that supercomputers might crack, they use pairs of entangled photons. Alice sends one photon from each pair to Bob while keeping its twin. Thanks to entanglement, these photons share a quantum bond measure one, and the other instantly mirrors its state. Now, if an eavesdropper, Eve, tries to intercept Alice's photons, she's forced to measure them, collapsing their delicate quantum states. The act of measurement disrupts the entanglement, creating telltale errors in the correlation between Alice and Bob's photons. Like a burglar leaving footprints in fresh snow, Eve's intrusion becomes glaringly obvious. The brilliance of this system isn't just its sensitivity to interference, it's the impossibility of cloning quantum information. Classical hackers might copy data packets unnoticed, but the no-cloning theorem of quantum mechanics forbids perfectly duplicating an unknown quantum state. Eve can't quietly replicate Alice's photons. She must interact with them, and that interaction leaves a trail. Real-world implementations, like China's Misha satellite, have already demonstrated this across record-breaking distances, beaming entangled photons to ground stations over 700 miles apart while maintaining flawless security. But the applications stretch far beyond secure messaging. Governments and financial institutions are eyeing quantum cryptography to protect everything from election systems to trillion-dollar transactions. In a world where cyberattacks grow more sophisticated by the day, entanglement offers something unprecedented: security rooted not in human-made algorithms, but in the unbreakable laws of quantum physics. Future quantum networks could link entire cities through unhackable channels, with each node acting as a sentinel, its entangled particles standing guard against digital intruders. Yet challenges remain. Quantum key distribution requires pristine conditions. Photons can't travel too far without being absorbed or scattered by the atmosphere. Researchers are tackling this with quantum repeaters, devices that extend entanglement's reach by stitching together shorter links into a seamless chain. Other teams are developing hybrid systems that blend quantum and classical encryption, offering practical security today while paving the way for a fully quantum internet tomorrow. The irony is delicious. The same phenomenon Einstein dismissed as spooky might soon become civilization's most trusted shield. In a universe where particles whisper secrets across vast distances, we're learning to speak their language and turning their mysteries into our greatest strength. Einstein's EPR paradox was meant to expose what he saw as quantum mechanics' fatal flaw, but instead, it became a beacon guiding us toward the theory's deepest mysteries. Today, physicists are still wrestling with the same question that troubled Einstein. How can particles instantaneously influence each other across vast distances without any signal passing between them? The answers they're proposing are as varied as they are mind-bending, each offering a radically different lens on entanglement's spooky action. Take Bohmian mechanics, for instance. This interpretation, developed by David Bohm in the 1950s, resurrects the idea of hidden variables not as Einstein imagined them, but as a pilot wave guiding particles along predetermined paths. In this view, entanglement isn't a coincidence. It's the result of an invisible quantum field orchestrating every particle's motion, like an unseen conductor ensuring every instrument in a cosmic symphony stays in tune. The catch, this quantum field responds instantaneously across the universe, making non-locality not just real but fundamental. Then there's relational quantum mechanics, championed by Carlo Rovelli. Here, reality isn't absolute, it's a web of relationships. A particle's properties don't exist in isolation. They're defined only in relation to other systems. Imagine two people describing a tree from opposite sides. One sees leaves, the other sees bark. Neither description is wrong, but neither is complete alone. Similarly, in Rovelli's framework, entanglement isn't a mysterious connection, it's just the universe reminding us that properties like spin or position only make sense when comparing one object to another. This dissolves the EPR paradox by suggesting there's no true state for distant particles to violate, just different perspectives on a relational tapestry. Meanwhile, proponents of objective collapse theories argue that wave functions aren't just mathematical tools, they're physical entities that spontaneously collapse over time without needing an observer. In this picture, entanglement's non-locality arises because the collapse happens everywhere at once, like a ripple spreading across a pond's surface. Some versions even tie collapse to gravity, suggesting spacetime itself plays referee in the quantum realm. It's a bold claim, but one that could explain why we never see cats both dead and alive. The universe has built-in mechanisms to prevent macroscopic weirdness. Yet for all their differences, these interpretations share a common thread. They force us to confront the unsettling idea that reality might not work the way our intuition insists. Whether through hidden waves, relational truths, or spontaneous collapses, they're all grappling with the same quantum riddle Einstein posed nearly a century ago. And as experiments push further testing loopholes, probing foundational principles, the debate only grows richer. Some physicists now speculate that entanglement might hint at a deeper structure beyond spacetime, while others wonder if we're glimpsing the shadows of a multiverse. One thing's certain, the EPR paradox wasn't the end of the story. It was the first clue in a mystery that's still unfolding, revealing a universe far stranger and far more connected than Einstein ever dreamed. What if you could take two particles that have never met, never touched, never even existed in the same corner of the universe, and instantly link their fates as if they'd been twins since birth? This isn't hypothetical, it's called entanglement swapping, and it's one of quantum physics' most astonishing party tricks. Here's how it works. Imagine two pairs of entangled particles. Let's call them pair A and pair B. Pair A consists of particle 1 and particle 2, while pair B is particle 3 and particle 4. Now, particles 2 and 3 have never interacted, but here's the twist. By performing a special measurement on particles 2 and 3 together, scientists can force the remaining particles 1 and 4 to become entangled despite having no direct connection. It's like introducing two strangers by showing them photos of their respective best friends shaking hands suddenly. They're linked through a bond they didn't forge themselves. This isn't just theoretical sleight of hand. Labs have demonstrated entanglement swapping using photons, the particles of light. In one experiment, researchers split entangled photon pairs and sent them to different locations. Then, by measuring two photons from separate pairs in a particular way, they teleported entanglement to the remaining photons miles apart. The implications are staggering. Normally, entanglement degrades over distance as photons get absorbed or scattered. But with swapping, you could daisy-chain entanglement across vast distances, like passing a quantum baton in a cosmic relay race. The real game changer, this could be the backbone of a quantum internet, a future network where information doesn't just travel, but teleports. Picture a globe-spanning web of entangled nodes, each connected through swapping. Send a message from New York to Tokyo, and it wouldn't traverse cables or satellites. It would hop through a series of quantum links, secured by the unbreakable laws of entanglement. Hackers couldn't intercept it without breaking the connection, making it the most secure communication system imaginable, but the potential goes beyond security. Entanglement swapping could enable quantum sensors of unprecedented precision, linking telescopes across continents to create a virtual observatory the size of Earth. Or imagine distributed quantum computing, where processors in different cities work as one giant machine, their qubits entangled through swapping to solve problems no single computer could crack. Of course, challenges remain. Swapping requires near-perfect synchronization and detection, and even a single lost photon can break the chain, yet progress is rapid. Recent breakthroughs have pushed swapping to work over hundreds of kilometers, with satellites poised to extend that range globally. What began as a laboratory curiosity is now the cornerstone of a quantum revolution, one where connections aren't just made but conjured from thin air. Quantum thermodynamics sounds like an oxymoron. How can the chaotic dance of particles obey the strict energy accounting of classical physics? Yet at the quantum level, the rules aren't just different, they're rewriting the textbooks. Take heat engines, those workhorses of thermodynamics that power everything from steam turbines to car engines. Classically, their efficiency is capped by the Carnot limit, a law etched in stone since the 19th century. But introduce entanglement, and suddenly those limits start to crumble. Imagine a quantum engine where the working fluid isn't steam or gas, but pairs of entangled particles. Because these particles share quantum information, they can coordinate their energy states in ways that defy classical intuition. Researchers have already designed theoretical models where entangled qubits extract more work from a heat bath than any classical system could, essentially cheating the Carnot limit by playing quantum poker with the universe. Then there's the bizarre case of negative temperatures. In everyday life, temperature is always positive. You can't get colder than absolute zero, but quantum systems don't play by those rules. When particles are entangled in specific configurations, their energy distribution flips upside down, creating states where adding energy actually decreases disorder. This isn't just a mathematical quirk, it's been observed in ultra-cold atomic lattices, where entangled spins behave as if they're hotter than infinity. Such systems could lead to quantum refrigerators that cool other components with unprecedented efficiency, or even exotic materials that absorb heat in reverse. The real shocker, entanglement entropy, might be the true currency of thermodynamics at the smallest scales. Classical entropy counts the number of ways particles can arrange themselves. Think of a deck of cards shuffled into random order. Quantum entropy, though, tallies the information shared between entangled particles. When two qubits entangle, their individual states become unknowable until measured, but their combined information grows richer. This trade-off, losing local certainty for global connection, could redefine how we understand energy flow. Some theorists now propose that black holes, those ultimate entropy factories, might owe their immense energy budgets to the quantum entanglement of particles at their event horizons. Practical applications are already on the horizon. Quantum heat pumps could one day cool quantum computers more efficiently than conventional methods, while entanglement-enhanced solar cells might capture sunlight with near-perfect efficiency by exploiting quantum coherence. Even time's arrow, the irreversible flow from order to disorder, gets a quantum twist. Experiments with entangled ions show that under certain conditions, quantum systems can temporarily reverse entropy's march, like a shattered glass reassembling itself. This isn't just tinkering at the edges of physics. It's a paradigm shift revealing that energy, work, and entropy aren't fundamental truths. They're emergent properties of a deeper quantum reality. And as we peel back those layers, we're finding that the universe's energy ledger isn't written in Newton's rigid script, but in the fluid, interconnected language of entanglement. Dark matter is the universe's most frustrating disappearing act, a ghostly substance that outweighs visible matter 5-1, yet refuses to interact with light or anything else we can detect. For decades, physicists have chased this cosmic phantom with giant detectors buried deep underground, hoping to catch a fleeting glimpse of its presence. But what if we've been looking in the wrong place? What if dark matter isn't just hiding in the shadows of the cosmos, but in the spooky connections of quantum entanglement? At first glance, the idea seems absurd. Dark matter's fingerprints are colossal, bending entire galaxies with its gravitational pull, while entanglement plays out on scales so tiny they're practically abstract. But dig deeper and strange parallels emerge. Both defy conventional detection: dark matter because it doesn't interact with light, and entanglement because measuring it destroys the delicate quantum states we're trying to observe. Both operate invisibly, yet their effects ripple across the universe. Could there be a hidden bridge between these two mysteries? One daring theory suggests dark matter might be composed of exotic particles that don't just pass through ordinary matter, but are entangled with it across vast distances. Picture a cosmic web where dark matter particles are quantum linked to visible ones, their gravitational influence not just a tug, but a synchronized dance dictated by entanglement. In this scenario, the reason dark matter seems to clump around galaxies isn't just gravity, it's quantum correlation, an invisible hand guiding its distribution. Some models even propose that dark matter's elusive nature stems from these particles being in a perpetual superposition, flickering in and out of detectable states like a light bulb stuck between on and off. Then there's the entangled dark energy hypothesis, which takes the speculation even further. If entanglement can create emergent spacetime, as some quantum gravity theories suggest, then perhaps dark energy, the force accelerating the universe's expansion, is a side effect of quantum correlation stretching across the cosmos. Imagine the vacuum of space not as empty nothingness, but as a seething quantum network where entangled pairs constantly form and annihilate. Dark energy, in this view, might be the tension of that network straining against itself, pushing the universe apart at the seams. Of course, these ideas are wildly speculative, skating on the thin ice of unproven physics. Critics argue that quantum effects are too fragile to persist across galactic scales, where thermal noise and decoherence would shred entanglement to ribbons. But supporters counter with a provocative question. What if dark matter isn't just influenced by entanglement? but is itself a relic of an ancient quantum phase transition. In the early universe, moments after the Big Bang, everything was hot, dense, and quantum coherent. As the cosmos cooled, most particles decohered, settling into the classical world we know. But dark matter, if it formed under unique conditions, might have preserved its quantum connections, freezing into a vast, entangled scaffold that still underlies the cosmos today. The beauty of these theories isn't just their audacity, it's their testability. Next-generation telescopes like the Vera Rubin Observatory could spot anomalies in dark matter's distribution, subtle clumps or voids that hint at quantum behavior. Meanwhile, tabletop experiments hunting for new forces between entangled particles might stumble upon signatures of dark matter's quantum handshake. Even if these ideas turn out to be dead ends, they're pushing physicists to ask new questions, bridging the gap between the infinitesimal and the infinite. Whether or not entanglement holds the key to dark matter, one thing is clear: the universe's greatest mysteries refuse to play by separate rules. From the quantum to the cosmic, the threads of reality might be woven tighter than we ever imagined, and the darkest corners of space could be hiding the brightest sparks of quantum revelation. Imagine a world where the secret to life's most efficient processes isn't just chemistry, but quantum physics. This is the radical promise of quantum biology, a field that's uncovering eerie hints that nature might have been mastering entanglement and superposition long before humans even dreamed of them. Take enzymes, those molecular machines that speed up chemical reactions in your body by factors of trillions. Classically, we'd expect them to work like locks and keys, relying on random collisions to find the right fit. But studies suggest some enzymes might use quantum tunneling, a phenomenon where particles vanish on one side of a barrier and reappear on the other, as if teleporting through an invisible shortcut. It's like a burglar walking through walls instead of picking locks, and it could explain how life achieves reactions at speeds and efficiencies that leave synthetic chemists in awe. Then there's the mystery of smell. How does your nose distinguish between molecules with nearly identical shapes? The standard lock and key model falls short, but quantum vibrations might hold the answer. Experiments show that fruit flies can tell apart molecules with the same shape but different hydrogen isotopes, a feat only possible if their antennae are sensitive to subtle quantum frequencies, like tiny tuning forks resonating with molecular bonds. Some researchers propose this as evidence that olfaction isn't just about molecular shape, but about electron tunneling and quantum interference, turning your nose into a biological quantum sensor. But the most provocative frontier lies in the brain. Could neural activity, the very substrate of thought, rely on quantum effects? The idea seems far-fetched. Brains are warm, wet, and noisy, hardly the pristine labs where quantum coherence thrives. Yet certain proteins in neurons, like microtubules, exhibit behaviors that classical physics can't fully explain. Anesthetics, which selectively shut off consciousness, seem to disrupt quantum coherence in these structures, while psychedelics enhance it. Even more striking, some birds navigate using Earth's magnetic field, possibly through entangled electron pairs in a protein called cryptochrome, a built-in quantum compass. The implications are staggering. If life has indeed been exploiting quantum tricks for billions of years, it would mean evolution isn't just a tinkerer, it's the ultimate quantum engineer, crafting solutions that blur the line between physics and biology. This challenges our assumptions about where quantum effects can thrive. We've long assumed they're fragile, confined to ultra-cold labs. But if nature harnesses them in the messy, bustling environment of a living cell, what other quantum marvels might be hiding in plain sight? Critics argue these effects are too fleeting to be biologically meaningful, or that classical explanations suffice. Yet the evidence keeps mounting. Photosynthesis, enzyme reactions, smell, navigation, each hints at a deeper quantum layer to life's machinery. Whether these are evolutionary masterstrokes or happy accidents, one thing's clear: the boundary between the quantum and the living is far more porous than we ever imagined. And if we can decode nature's quantum playbook, it might revolutionize everything from medicine to energy, proving once again that the universe's strangest phenomena aren't just out there in the cosmos, they're woven into the fabric of life itself. The universe might not just contain entanglement, it might be entanglement, woven together from the smallest particles to the grandest galactic clusters. Picture the Big Bang not as a fiery explosion in empty space, but as a quantum event where every particle was born deeply connected, like strands in a cosmic tapestry. In those first moments, the entire cosmos could have existed in a state of perfect quantum unity, a sea of particles so entangled that the idea of separate places or objects would have been meaningless. Over time, as the universe expanded and cooled, most of those connections faded into the background, but their ghostly imprint might still linger, etched into the very structure of reality. Take the cosmic web, the vast network of galaxies and dark matter that stretches across the observable universe. At first glance, its intricate filaments and voids seem sculpted by gravity alone. But look closer and peculiar patterns emerge. The distribution of galaxies isn't entirely random. There are correlations on scales so large that gravity alone can't explain them. Some theorists propose these anomalies are cosmic fossils, remnants of quantum entanglement from the universe's infancy. In this view, the seeds of galaxy clusters weren't just planted by random fluctuations in the early universe, but by quantum connections that stretched across primordial space, guiding matter into clumps and threads that still echo those ancient bonds today. The math behind this idea is as elegant as it is mind-bending. Quantum field theory suggests that the vacuum of space isn't truly empty. It's a seething foam of virtual particles popping in and out of existence, entangled in an endless dance. During inflation, the period of rapid expansion just after the Big Bang, these quantum fluctuations could have been stretched to cosmic proportions, imprinting their entangled patterns onto the density of matter. It's as if the universe's largest structures, superclusters, filaments, even the Great Wall of galaxies, are shadows cast by quantum handshakes forged in the first trillionth of a second. Even black holes, those cosmic vacuum cleaners, might be knots in this quantum network. The holographic principle suggests that all the information inside a black hole is encoded on its event horizon, with entanglement threads linking each bit on the surface to its counterpart deep inside. Scale this up, and the entire universe could be a hologram. It's three-dimensional reality projected from a two-dimensional boundary where entanglement does the heavy lifting. If true, then the cosmos isn't just held together by gravity or dark matter. It's stitched together by quantum correlations, with every star, planet, and atom connected in a web more intricate than we ever imagined. The implications are staggering. If entanglement built the universe, then the very notion of distance might be an illusion. Two galaxies on opposite sides of the sky could, in some deeper sense, still be quantum neighbors, their fates intertwined since the dawn of time. This might explain mysteries like quantum non-locality, where particles instantly influence each other across vast distances. They're not really far apart in the quantum code underlying reality. Some physicists even speculate that dark energy, the force accelerating the universe's expansion, could be the tension of this quantum network straining against itself, like a rubber sheet stretched too thin. Yet for all its beauty, the idea remains fiercely debated. critics argue that entanglement is too fragile to survive the chaos of the early universe, let alone shape it billions of years later. But new tools are emerging to test these ideas. Future telescopes could hunt for subtle statistical quirks in the cosmic microwave background, the afterglow of the Big Bang, that betray the fingerprints of primordial entanglement. Others propose tabletop experiments where entangled particles simulate the universe's expansion, offering clues about how quantum links behave under extreme conditions. Whether or not these theories hold, one thing's clear: entanglement isn't just a quirk of tiny particles. It might be the hidden architecture of everything, from the atoms in your hand to the galaxies spinning in the void. The universe, it seems, isn't a collection of isolated objects. It's a single, shimmering quantum network, whispering to itself across the eons. Time crystals sound like something ripped from a science fiction novel, structures that pulse and oscillate not in space, but in time, like a heartbeat woven into the fabric of reality itself. Unlike ordinary crystals, where atoms arrange themselves in repeating patterns across 3 dimensions, time crystals introduce a 4th dimension. They're periodic, not just in space, but in time. Imagine a diamond that doesn't just sit on a shelf, it breathes, cycling through its atomic configurations over and over without any energy input. This isn't perpetual motion. It's a quantum dance where entanglement serves as the choreographer, guiding particles into rhythms that defy classical physics. The secret lies in how time crystals exploit entanglement to break time symmetry, a fundamental principle that says the laws of physics should remain unchanged whether time moves forward or backward. Normally, if you flip the arrow of time, a system should retrace its steps like a movie played in reverse, but time crystals don't play by those rules. Their oscillations persist even when the system is in its lowest energy state, a phenomenon made possible by the quantum links between their constituent particles. Picture a row of entangled pendulums, each swaying in perfect sync without any external push. Measure one, and the others instantly adjust their rhythm, not because of some hidden force, but because their fates are quantum mechanically intertwined. This bizarre behavior was first proposed in 2012 by Nobel laureate Frank Wilczek, but skeptics dismissed it as impossible until experiments in 2017 proved otherwise. Using chains of trapped ions or diamond impurities, researchers created the first time crystals, observing their telltale oscillations under laser pulses. The key ingredient, entanglement. Without it, the particles would quickly settle into equilibrium, their motion dampening like a wound-down clock. But entangled particles resist this decay, their quantum connections acting like invisible springs that keep the system forever ticking. The implications stretch far beyond theoretical curiosity. Time crystals could revolutionize quantum computing by serving as ultra-stable quantum memory, their inherent rhythm protecting information from decoherence, the bane of quantum systems. Imagine a quantum hard drive that doesn't just store data, but actively preserves it through self-sustaining cycles. Or consider sensors capable of detecting infinitesimal magnetic fields, their entangled time crystal arrays amplifying signals with unrivaled precision. Yet the most tantalizing possibility lies in time itself. If entanglement can birth structures that defy time's arrow, what does that say about the nature of reality? Some theorists speculate that time crystals might be glimpses of a deeper physics, where time isn't a backdrop but an active participant, shaped by quantum correlations. Others wonder if they could model exotic cosmic phenomena, like pulsars or even the universe's own cyclical rhythms. One thing's certain: time crystals blur the line between the quantum and the cosmic, proving once again that entanglement isn't just a microscopic curiosity. It's a sculptor of reality, carving order from chaos and rhythm from stillness. And as we unravel their secrets, we're not just discovering a new phase of matter, we're rewriting the rules of time itself. Quantum Darwinism flips the script on how we perceive reality. It's not that the universe chooses definite states, but that certain quantum states survive and thrive while others fade into obscurity. Think of it like natural selection, but for quantum possibilities. In the microscopic world, particles exist in a haze of superpositions, multiple states at once, until they interact with their environment. But here's the twist: not all interactions are created equal. Some quantum states become entangled with countless particles in the surroundings, spreading their influence like a meme going viral. These fittest states are the ones we end up measuring, the ones that appear classical. The rest, they're drowned out by the noise of the universe, collapsing not because of some mystical observer, but because they couldn't keep up in the quantum competition for survival. Take Schrödinger's cat again. In the many worlds interpretation, the cat is both alive and dead, with each outcome branching into a separate universe. But quantum Darwinism offers a different answer. The cat state isn't split, it's filtered. The moment the box interacts with the environment, whether through air molecules, stray photons, or even the faintest vibrations, countless tiny entanglements form. These interactions amplify one outcome, say, a purring cat, while suppressing the other, a lifeless one, not because of conscious observation, but because the alive state builds stronger correlations with the world outside the box. What we perceive as a definite reality is just the quantum equivalent of the loudest voice in a crowded room. This idea reshapes how we think about quantum to classical transitions. Decoherence, the process that destroys quantum superpositions, isn't just a nuisance, it's the mechanism of quantum selection. Imagine tossing a pebble into a pond. The ripples spread, entangling with the water's surface, the air above, even the shore. Soon, the pebble's initial splash is inseparable from its environment. Similarly, when a quantum system entangles with its surroundings, its fragile superpositions leak into the environment, leaving behind only the most stable, redundantly encoded states. These are the states we measure, the ones robust enough to leave an imprint on the world. The implications are staggering. If quantum Darwinism holds, then the solidity of the everyday world, the chair you're sitting on, the screen in front of you, isn't fundamental. It's an emergent property, a collective hallucination forged by countless quantum interactions. Even time's arrow might be a byproduct of this Darwinian winnowing, with the past appearing fixed because those quantum states were the ones that successfully reproduced their information into the future. Critics argue this doesn't fully solve the measurement problem, why we perceive this particular outcome and not another. But supporters counter that it's not about explaining consciousness, it's about explaining stability. The universe isn't trying to show us a classical world. It's just that the classical world is what sticks around long enough to be seen. From this perspective, reality isn't a single, objective truth. It's the quantum equivalent of a consensus, a story told by the most persistent correlations in the cosmic noise. And that story, it turns out, is the one we're all living in. Beneath the surface of everyday materials, the steel in your car, the silicon in your phone, lies a hidden quantum landscape where particles don't just interact but dance in perfect, entangled synchrony. This isn't just theoretical whimsy, it's the frontier of condensed matter physics, where entanglement is rewriting the rules of what matter can do. Take topological order, a phenomenon that transforms humble electrons into collective states with memory so robust, it's practically immune to errors. Picture a material where electrons don't just buzz around randomly but weave themselves into intricate quantum braids. These braids aren't just beautiful abstractions, they're physical lifelines. tug on one end and the other responds instantly, not because of some signal, but because the entire system is entangled into a single, unbreakable knot. This isn't science fiction. It's the reality of topological insulators, materials that conduct electricity flawlessly along their edges while remaining stubbornly inert inside, all thanks to entanglement's invisible hand. Then there are quantum spin liquids, materials that refuse to settle down even at absolute zero. In ordinary magnets, electron spins align neatly like soldiers in formation when cooled. But in these exotic states, entanglement keeps the spins perpetually tangled, like a crowd of commuters at rush hour, each jostling but never finding a seat. The result, a material that never freezes into order, where disturbances don't travel as waves or particles but as fractionalized entities called enyons. These enyons have a bizarre property. They remember their history as they move, like hikers leaving glowing footprints in the dark. That memory isn't stored locally but distributed across the entire entangled network, making these materials prime candidates for fault-tolerant quantum computers. Imagine a processor where errors don't cascade into chaos because the information isn't stored in fragile bits, but woven into the fabric of the material itself. The implications stretch far beyond the lab. High-temperature superconductors, those elusive materials that conduct electricity without resistance at relatively balmy temperatures, might owe their magic to entangled electron pairs. Normally, superconductivity requires extreme cold to keep electron pairs in sync. But in certain copper-based compounds, entanglement could be gluing pairs together more resiliently, like dancers whose movements stay perfectly matched even as the room warms. If we can crack this code, we might unlock room-temperature superconductors, materials that could revolutionize energy grids, levitating trains, even medical imaging. What's most astonishing is how these discoveries blur the line between the quantum and the tangible. We're not just talking about lone particles in a vacuum. We're talking about bulk materials you could hold in your hand, where entanglement isn't a fragile curiosity but the bedrock of their behavior. This isn't just physics, it's alchemy for the quantum age, turning ordinary matter into platforms for technologies that sound like they're ripped from the future. And as we dig deeper, who knows what other entangled wonders are waiting, hidden in the atomic lattices of the world beneath our feet. The Copenhagen interpretation, born from the fiery debates between Niels Bohr and Werner Heisenberg in the 1920s, treats quantum mechanics like a grand cosmic game of peekaboo. In this view, particles don't have definite properties until measured. They exist in a haze of probabilities, with entanglement acting as the universe's way of keeping its options open. Picture flipping a coin that only decides whether it's heads or tails the moment you catch it. Now imagine two such coins, flipped together but landing miles apart, yet always matching perfectly. That's entanglement under Copenhagen, a correlation without any hidden mechanism, a fundamental randomness that's baked into reality itself. Bohr famously said, "If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet." For Copenhagenists, entanglement isn't a puzzle to solve, it's a feature to accept, a reminder that the quantum world operates on rules that defy our classical intuition. But not everyone is content with this surrender to mystery. Enter cubism, short for quantum Bayesianism, a radical reinterpretation that puts the observer front and center. Here, quantum probabilities aren't statements about the world, but about our beliefs as observers. Think of it like weather forecasts. When a meteorologist says there's a 70% chance of rain, they're not describing some objective property of the atmosphere. They're expressing confidence based on available data. Cubism applies this logic to quantum states, treating entanglement as a tool for updating personal expectations, not as a physical link between particles. If Alice measures one entangled photon and finds it polarized vertically, cubism says her knowledge about its distant twin updates instantly, not because any signal traveled faster than light, but because her certainty about the system changed. It's quantum mechanics as a user manual for prediction, not a blueprint of reality. Then there's the camp that refuses to give up on determinism entirely. Objective collapse theories, like Roger Penrose's gravitational or model, propose that wave functions aren't just mathematical tools, they're physical entities that spontaneously collapse when they reach a certain threshold, with gravity acting as the trigger. In this picture, entanglement's spooky action is a fleeting phenomenon, doomed to collapse under its own weight. Picture a house of cards. The larger the quantum system, the more unstable its superposition becomes, until gravity steps in like a gust of wind, forcing it to settle into a single state. Penrose suggests this might happen continuously in the brain, with microtubules hosting tiny quantum collapses that give rise to consciousness itself. It's a wild idea, but one that offers a tantalizing escape from the measurement problem. No observers needed, just good old-fashioned spacetime curvature. The stakes in these debates couldn't be higher. If Copenhagen is right, reality is fundamentally fuzzy until observed, a notion that smacks of solipsism to some. If cubism prevails, physics becomes a deeply personal affair, where probabilities reflect individual perspectives rather than universal truths. And if objective collapse theories gain traction, we might finally bridge the gap between quantum weirdness and the solid, predictable world we experience daily. Experimentalists are already devising tests to probe these interpretations, from lab-scale gravity sensors that could catch a wave function mid-collapse to AI-driven analyzers of quantum data that might reveal hidden Bayesian patterns. What's fascinating is how entanglement serves as the litmus test for each interpretation. For Copenhagen, it's the ultimate example of quantum non-locality. For cubism, it's a lesson in how information updates across correlated systems. And for collapse theories, it's a fragile state destined to shatter under the weight of reality. The battle isn't just academic, it's shaping the next century of physics, from the design of quantum computers to our search for a theory of everything. After all, if we can't agree on what entanglement means, how can we hope to understand the universe it's woven into? Quantum sensors are rewriting the rules of measurement, turning what was once science fiction into everyday reality. And at the heart of this revolution lies entanglement. Imagine a device so precise it can detect the faintest whisper of a gravitational wave rippling through space-time, or measure time with such accuracy that it would take 15 billion years to lose a single second. This isn't hypothetical. Atomic clocks, the gold standard of timekeeping, now harness entangled atoms to smash through the standard quantum limit, a barrier once thought unbreakable. By linking atoms in a quantum dance, these clocks don't just average out individual errors, they cancel them entirely, as if the atoms themselves are conspiring to reveal time's true flow. The magic lies in entanglement's ability to synchronize particles beyond classical limits. Take gravitational wave detectors like LIGO, which listen for the cosmic echoes of colliding black holes. Normally, the Heisenberg uncertainty principle dictates a trade-off. Measure a particle's position precisely, and its momentum becomes a blur. But entangle the photons used in LIGO lasers, and suddenly that uncertainty isn't just a limit, it's a resource. These photons, linked across kilometers of vacuum, act as a single quantum entity, allowing the detector to sense space-time trembles smaller than 1,000th of a proton's width. It's like trying to hear a pin drop in a hurricane, only to realize the storm's chaos is the very thing that sharpens your ears. In medicine, quantum sensors are poised to transform diagnostics. Traditional MRI machines require powerful magnetic fields to peer inside the body, but entangled nitrogen vacancy centers in diamonds could one day DETECT Chinese letter, 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 Chinese letter procedures. These microscopic quantum compasses, sensitive to the faintest magnetic fields, might soon map neural activity with unprecedented resolution, uncovering the electrical storms behind conditions like epilepsy or Alzheimer's. Even underground, oil companies are testing quantum gravimeters devices that use entangled atoms to measure minuscule variations in gravity, revealing hidden oil reserves without drilling a single well. Perhaps the most profound applications lie in fundamental physics. Quantum sensors could hunt for dark matter by spotting its ghostly gravitational tug, or test whether Einstein's equivalence principle, the idea that gravity affects all objects equally, holds true at quantum scales. Some experiments are already using entangled atoms to probe the fabric of spacetime itself, searching for hints that gravity might emerge from quantum entanglement, as some theories suggest. What makes these sensors so revolutionary isn't just their precision, it's their defiance of classical intuition. They don't merely push boundaries, they redefine what boundaries even mean. In a universe where particles can whisper to each other across vast distances, the act of measurement isn't about observing the world, it's about collaborating with it, using entanglement as a bridge between what we can see and what's been hiding in plain sight all along. Where exactly does the quantum world end and our familiar classical reality begin? It's a question that's haunted physicists for decades, and the answer is far murkier than you might expect. We've long assumed that quantum weirdness, superposition, entanglement, wave-particle duality fizzles out as objects grow larger, leaving behind the predictable, clockwork universe we know. But groundbreaking experiments are shattering that assumption, revealing that the boundary between quantum and classical isn't a clear line, it's a shifting frontier, one where even objects visible to the naked eye can, under the right conditions, dance to the quantum tune. Take the famous double-slit experiment, where particles like electrons create an interference pattern as if they're waves passing through both slits simultaneously. In the 1990s, scientists pulled off this trick with buckeball soccer ball-shaped molecules made of 60 carbon atoms. These weren't solitary electrons, they were complex structures, yet they still behaved as quantum waves. Fast forward to 2019, and researchers pushed the envelope even further, demonstrating wave-like interference with molecules 2,000 times heavier than a buckeball. These weren't just particles, they were tiny machines, and yet, when isolated from environmental noise, they defied classical intuition, proving that quantum behavior isn't confined to the microscopic. But the real shock came when scientists began probing macroscopic systems. In 2021, a team at ETH Zurich entangled a vibrating membrane with a cloud of atoms, a setup where one component was visible under a microscope. The membrane, though tiny, was a classical object by everyday standards, yet it exhibited quantum coherence, its motion inextricably linked to the atomic cloud through entanglement. This wasn't just a lab curiosity, it was a glimpse into how quantum effects might persist or dissolve as we scale up. The key to these experiments lies in mastering decoherence, the process by which quantum superpositions collapse into definite states. Picture a drop of ink in water. At first, it holds its shape, but as it interacts with the surrounding molecules, it spreads and fades. Quantum systems work similarly. Their delicate superpositions leak into the environment, destroyed by even the slightest disturbance. But by cooling systems to near absolute zero and shielding them from vibrations, researchers can slow decoherence to a crawl, preserving quantum behavior in larger and larger objects. What's emerging is a startling picture. The quantum classical boundary isn't about size alone. It's about isolation, temperature, and how tightly a system's components are entangled. In some theories, even living organisms under impossibly ideal conditions could exhibit quantum effects. The line between the strange and the familiar isn't just blurry. It might be a matter of perspective, a reminder that the universe doesn't operate in two separate rulebooks. There's just one physics, and we're only beginning to understand where its quantum roots end and our classical experience begins. Imagine a hard drive that doesn't just store ones and zeros, but entire quantum states, delicate, entangled configurations that could teleport information across continents or power a quantum computer's unfathomable calculations. This is the dream of quantum memories, devices designed to capture and preserve entanglement like fireflies in a jar. Unlike classical memory, which can copy data endlessly, quantum memory must cradle superposition and entanglement without collapsing them, a feat akin to balancing a house of cards in a hurricane. The stakes couldn't be higher. Without reliable quantum storage, the grand visions of a quantum internet or scalable quantum computing remain out of reach. One of the most promising approaches uses individual atoms, suspended in near-perfect isolation by laser beams or magnetic fields. Picture a single rubidium atom held in an optical trap, its outermost electron orbiting in a fragile quantum state. By entangling this atom with a photon, researchers can effectively write quantum information into its atomic memory. The challenge, keeping that atom still long enough to read the information back out. Even the faintest jostle, a stray photon, a whisper of heat, can destroy the entanglement. To combat this, scientists cool atoms to near absolute zero and shield them in vacuum chambers, creating conditions so pristine that quantum states can persist for seconds or even minutes, an eternity in the quantum realm. Ions, atoms with an electric charge, offer another tantalizing path. Trapped in electromagnetic fields and cooled to a near standstill, ions can be entangled using precisely tuned laser pulses. Their advantage: stubborn coherence. In some experiments, entangled ions have maintained their quantum links for over an hour, a record that makes them frontrunners for quantum repeaters devices that extend entanglement's reach across fiber optic networks. The trade-off: ions are finicky. Aligning lasers to manipulate them without introducing noise is like performing microsurgery with chopsticks. Yet labs are making strides, with companies like IonQ already integrating trapped ion memories into early quantum computers. Solid-state systems, meanwhile, are the dark horses of the race. Think diamond crystals with tiny imperfections, nitrogen vacancy centers, where electrons can be coaxed into entangled states. Unlike atoms or ions, these systems don't require elaborate traps or ultra-high vacuums. They're rugged enough to imagine slotting into existing technology. The catch: their quantum states are easily drowned out by the crystal's own vibrations. Researchers are tackling this by engineering purer diamonds or using clever error correction codes, effectively teaching the memory to ignore the noise. Recent breakthroughs have pushed solid-state coherence times into the millisecond range, edging closer to practicality. The Holy Grail, a hybrid system that marries the best of all worlds: atoms' coherence, ion stability, and solid-state scalability. Imagine a quantum hard drive where information hops from trapped ions to diamond, chips to photonic circuits, each platform optimized for a different task. Some prototypes already hint at this future, like quantum buffers that convert fleeting photonic entanglement into stable atomic storage before shunting it back to light for transmission. The implications ripple far beyond labs. A working quantum memory could revolutionize secure communication, enabling unhackable networks where data is teleported, not transmitted. It could turbocharge quantum computers, letting them pause mid-calculation to store intermediate results, a feat impossible today. And it might even answer fundamental questions about decoherence itself, revealing how the quantum universe gives way to the classical one we perceive. The race isn't just about technology, it's about rewriting the rules of information itself. Whoever cracks quantum memory won't just build a better hard drive, they'll unlock a new layer of reality, one where distance is an illusion and information is as ephemeral and as enduring as a whisper in the quantum wind. What if the very fabric of consciousness, your thoughts, your memories, the spark of awareness that makes you you, is woven from the same quantum threads that bind particles across the cosmos? It's a radical idea, one that blurs the line between mind and matter in ways that make even seasoned physicists uneasy. At the heart of this controversy lies orchestrated objective reduction, or ORCH, or a theory championed by Nobel laureate Roger Penrose and anesthesiologist Stuart Hameroff. They propose that consciousness isn't just a byproduct of neural activity, but a quantum phenomenon arising from microtubules, tiny protein structures inside brain cells, where entanglement and wave function collapse play out on a microscopic stage. Picture this: inside every neuron, microtubules act like quantum processors, their tubulin proteins flipping between states in superposition. According to ORCH, these quantum vibrations don't just flicker randomly, they coordinate across vast networks through entanglement, collapsing into definite states in a way that generates moments of conscious experience. Penrose ties this collapse to gravity, suggesting spacetime itself becomes unstable at tiny scales, forcing quantum superpositions to choose a reality. In this view, your stream of awareness isn't just electrical impulses, it's a symphony of quantum collapses, each note resonating across the entangled web of your brain. The implications are staggering. If ORCH holds, consciousness wouldn't be confined to brains alone. It might be a fundamental feature of the universe, with entanglement serving as its substrate. This echoes ancient panpsychist philosophies, where mind isn't emergent but intrinsic to matter. But here's the catch: most physicists dismiss these ideas as speculative at best, pseudoscience at worst. The brain, they argue, is too warm, too wet, too chaotic for delicate quantum states to survive. Decoherence, the enemy of quantum coherence, would shred these fragile superpositions in nanoseconds, long before they could influence cognition. Experiments showing quantum effects in photosynthesis or bird navigation don't translate to the noisy, bustling environment of neurons. Skeptics also point to Occam's razor. Why invoke quantum mechanics when classical neuroscience explains so much? Consciousness could simply be an emergent property of complex neural networks, no spooky action required. Yet ORCH supporters counter with a provocative question. If entanglement underpins reality at its core, why wouldn't evolution exploit it? They point to anesthetics as curious evidence. These chemicals selectively shut off consciousness while sparing other brain functions, and they just happen to disrupt quantum coherence in microtubules. Psychedelics, which alter perception, seem to enhance it. Coincidence or clue? The debate reveals a deeper tension in science: how to reconcile the subjective richness of consciousness with the cold equations of physics. Entanglement, for all its strangeness, offers a tantalizing bridge, but one most researchers hesitate to cross. Even if ORCH is wrong, it forces us to confront how little we understand about the mind's relationship to the quantum world. Could entanglement be the missing piece in the puzzle of awareness? Or is this just another case of quantum mysticism, dressing up metaphysical claims in the language of physics? For now, the idea remains on the fringes, but fringe ideas have a habit of reshaping science. After all, entanglement itself was once dismissed as spooky before becoming the cornerstone of quantum technologies. Whether or survives scrutiny or collapses under it, one thing's clear: the intersection of quantum physics and consciousness isn't just a scientific frontier. It's a mirror reflecting our deepest questions about what it means to exist in a universe where matter and mind might be far stranger and far more connected than we ever imagined. Quantum simulations are like giving the universe a mirror, allowing it to study its own deepest secrets through the strange dance of entangled particles. While classical computers choke on the complexity of quantum systems, their calculations ballooning exponentially with each additional particle, quantum simulators embrace the chaos, turning entanglement into their greatest asset. Picture trying to predict how hundreds of electrons will interact in a high-temperature superconductor. On a classical machine, this requires tracking each electron's possible states individually, a task so monstrous it could take longer than the age of the universe. But a quantum simulator, it sidesteps the problem entirely by becoming the very system it's modeling, with entangled qubits standing in for the electrons, their natural quantum behavior mirroring the physics at play. Take the hunt for room-temperature superconductors, one of materials science's holy grails. These elusive materials could transmit electricity without resistance, revolutionizing power grids and transportation, but their quantum mechanics are fiendishly complex. Enter quantum simulators, devices like ultra-cold atom arrays, where lasers trap atoms in precise lattices, and magnetic fields nudge them into entangled states that mimic superconducting electrons. Already, experiments have uncovered tantalizing clues about how electron pairs might form and move in these materials, insights no supercomputer could reliably provide. It's as if we've traded in a blurry telescope for an electron microscope, revealing quantum correlations hidden in plain sight. The magic extends to quantum chemistry, where simulating even simple molecules pushes classical machines to their limits. Consider nitrogenase, the enzyme soil bacteria used to break nitrogen bonds, a process critical for fertilizer production. Industrially, we replicate this in energy-guzzling factories because we've never fully understood the quantum choreography at nitrogenase's active site. Quantum simulators, though, can recreate those molecular conditions by entangling qubits to represent atomic orbitals, letting researchers watch quantum tunneling and electron sharing unfold in real time. The payoff: cleaner, cheaper industrial chemistry, designed with quantum precision. But perhaps the most mind-bending applications lie in lattice gauge theories, the mathematical frameworks describing how fundamental forces like the strong nuclear force bind quarks inside protons and neutrons. These equations are so nonlinear that even supercomputers approximate them with crude simplifications. Quantum simulators, however, can engineer tabletop experiments where entangled ions or superconducting circuits act as stand-ins for quarks and gluons, their interactions mirroring the physics of a tiny, artificial universe. Recent breakthroughs have used these setups to observe phenomena like quark confinement, the very reason you can't pluck a quark free from a proton, offering a sandbox to test theories that would otherwise remain abstract scribbles on a chalkboard. What makes these simulations so revolutionary isn't just their brute force power, it's their elegance. They don't compute quantum behavior, they embody it, leveraging entanglement to explore realms where traditional math falters. Some physicists now speculate that quantum simulators might one day tackle problems we don't even know how to frame classically, from the quantum dynamics of black hole horizons to the emergence of spacetime itself. In that sense, simulation isn't just entanglement's killer app, it's a bridge to realities we're only beginning to imagine. The quantum revolution isn't looming on the horizon. It's already unfolding in labs and data centers around the world, rewriting the rules of what technology can achieve. At the heart of this transformation lies entanglement, the same phenomenon that once baffled Einstein, now poised to power breakthroughs that sound ripped from the pages of a sci-fi novel. Picture a quantum internet, not just a faster version of today's web, but an entirely new kind of network where information doesn't travel, it teleports. Researchers in China have already demonstrated the groundwork, using satellites to beam entangled photons across continents, enabling secure communication that's immune to hacking by the laws of physics itself. This isn't just about speed, it's about redefining connectivity, creating a global system where data moves instantaneously, encrypted by the unbreakable handshake of entangled particles. But the quantum internet is just the beginning. Imagine fault-tolerant quantum computers, machines so robust they can shrug off the errors that plague today's fragile qubits. Current quantum processors are like delicate glass sculptures, their calculations crumbling at the slightest disturbance. The solution: topological qubits, exotic particles like anyons that store information not in individual states, but in the braided paths they trace through spacetime. These aren't just theoretical curiosities. Companies like Microsoft are betting millions on their potential, aiming to build quantum machines that correct their own errors by weaving entanglement into the very fabric of their design. It's a leap from today's noisy, error-prone systems to a future where quantum computers could simulate complex molecules for drug discovery or optimize global supply chains in minutes. Yet for all this promise, the path forward is strewn with obstacles. Scaling up quantum systems isn't just a matter of adding more qubits, it's a battle against decoherence, the relentless process that tears apart entangled states like a gust of wind scattering smoke. Engineers are fighting back with innovations like cryogenic cooling and error-correcting codes, but the challenge is monumental. Even maintaining entanglement between a few dozen qubits requires conditions more controlled than deep space. And then there's the issue of control. Manipulating entangled particles without disturbing their delicate states is like performing brain surgery with oven mitts. The breakthroughs on the horizon, though, make these hurdles worth surmounting. Quantum sensors could one day map underground mineral deposits with pinpoint accuracy or detect stealth aircraft by their gravitational shadows. Quantum simulations might unlock the secrets of high-temperature superconductors, materials that could slash global energy consumption, and entangled networks could synchronize clocks across continents with such precision that GPS becomes obsolete, replaced by a quantum timekeeping grid accurate to a billionth of a second. What's most exhilarating is how much we don't yet know. Entanglement's full potential might still be hidden, waiting for some future innovator to uncover applications we can't yet imagine. The quantum future isn't just about faster computers or secure networks, it's about discovering a new layer of reality, one where distance is an illusion and information flows in ways that defy classical logic. The only certainty: entanglement will be the thread stitching it all together, a quantum seam running through the fabric of tomorrow's technology. Quantum technologies promise to reshape our world, but with that power comes a responsibility humanity has never faced before. Picture a future where a quantum computer could crack the encryption safeguarding online banking, medical records, and national security communications in minutes. The same algorithms that might one day design life-saving drugs could also unravel the digital foundations of modern society. This isn't speculative fiction, it's a tangible risk as quantum processors scale up. Cryptographers are already racing to develop post-quantum encryption, new mathematical frameworks resistant to quantum attacks, but the transition is a global game of catch-up. Banks, governments, and tech giants must overhaul their systems before quantum adversaries render today's security obsolete. The stakes couldn't be higher. A single breakthrough in the wrong hands could expose the world's data to chaos. Then there's the specter of quantum warfare. Imagine satellites equipped with entangled photon emitters, enabling unhackable communication networks for militaries, or worse, sensors capable of detecting stealth submarines by measuring disturbances in Earth's gravitational field. The same entanglement that powers ultra-secure messaging could also create unbreakable surveillance systems, where every encrypted transmission is intercepted and stored until quantum computers can decrypt them retroactively. Nations are investing billions in quantum defense initiatives, but the line between protection and domination blurs quickly. History shows that technological superiority often fuels arms races. Quantum tech could escalate conflicts at light speed, quite literally, if entangled particles become tools for instant, untraceable attacks. Beyond security, entanglement raises profound questions about privacy and autonomy. Quantum sensors might one day map human brain activity with such precision that they decode thoughts, a tool for medical breakthroughs or a dystopian nightmare. Could governments or corporations exploit quantum-enhanced AI to predict behavior by analyzing entangled neural patterns? The ethical boundaries here are uncharted. Even quantum simulations designed to model climate change or economic systems could inadvertently manipulate markets or ecosystems if wielded without oversight. Unlike classical technologies, quantum systems operate in realms where cause and effect aren't always linear, making accountability a labyrinthine challenge. Yet the most urgent dilemma lies in access. Quantum advantages could deepen global inequalities if only a handful of nations or corporations control the technology. Imagine a world where quantum-powered AI designs all new medicines, but patents lock them behind paywalls, leaving poorer nations without life-saving treatments. Or consider quantum farming sensors that optimize crop yields but are owned by agribusiness monopolies, squeezing out small farmers. The risk isn't just misuse, it's exclusion. Without international cooperation, the quantum age could fracture society into haves and have-nots, where entanglement becomes another tool of division rather than unity. The path forward demands more than innovation. It requires a new ethical framework. Scientists, policymakers, and philosophers must collaborate to establish guardrails before quantum capabilities outpace our wisdom. Transparency in research, open dialogues about military applications, and equitable access to quantum infrastructure are no longer optional, they're existential. The same entanglement that binds particles across space might also bind humanity's fate to the choices we make today. Will we harness quantum wonders to heal, connect, and elevate, or let them become instruments of control and chaos? The answer lies not in the lab, but in the collective conscience of a species standing on the brink of a new frontier. One of the biggest myths about quantum entanglement is that it allows for faster-than-light communication, a sci-fi fantasy that even Einstein himself wrestled with. While it's true that measuring one entangled particle instantly affects its partner, no actual information is transmitted between them. Think of it like opening a sealed envelope containing two slips of paper, one reading yes and the other no. No matter how far apart you separate the slips, the moment you peek at one, you know the other, but you haven't sent a signal. The universe isn't breaking its own speed limit. It's revealing a pre-existing correlation hidden in the quantum fine print. Another persistent misconception is that entanglement could explain telepathy or supernatural connections between minds. While the idea of quantum consciousness makes for gripping fiction, there's zero evidence that human thoughts or emotions are governed by quantum entanglement. The brain operates at temperatures far too warm and chaotic to sustain delicate quantum states for meaningful periods. Those claiming entanglement bridges human consciousness often confuse metaphor with mechanism, like mistaking a poet's description of love as electric for literal bioelectrical engineering. Then there's the oversimplification that entangled particles are just magically linked. In reality, their connection stems from rigorous mathematical relationships, not mystical forces. When particles entangle, their quantum states become interdependent, described by equations that respect strict conservation laws. It's less a cosmic friendship and more an unbreakable contract written in the language of probability amplitudes. This distinction matters because it shifts entanglement from the realm of magic to the realm of engineering, something we can harness, not just marvel at. A subtler myth suggests that entanglement defies causality, allowing future events to influence the past. While quantum mechanics does challenge classical notions of time, like in delayed choice experiments, entanglement itself doesn't create time loops or backward causation. Correlations between particles are set up at the moment they entangle, and any subsequent measurements merely reveal those pre-established links. It's not that the universe is rewriting history, it's that our classical intuition about cause and effect is too rigid to capture quantum reality. Perhaps the most dangerous misconception is that entanglement makes quantum computers omnipotent. Yes, they excel at specific tasks like factoring large numbers or simulating molecules, but they won't instantly solve all of humanity's problems. Entanglement alone doesn't guarantee computational power. It's just one tool in a quantum algorithm's toolkit. Overhyping its capabilities risks disillusionment when quantum computers don't instantly cure cancer or crack all encryption. The truth is messier, slower, and far more interesting. Entanglement is a resource, not a miracle. Dispelling these myths isn't just academic, it's essential for navigating the quantum age responsibly. When public understanding lags behind the science, pseudoscience rushes in to fill the void. By grounding entanglement in its real-world physics, we empower people to engage with quantum technologies critically, whether they're evaluating a headline, voting on research funding, or simply marveling at the universe's strangeness without mistaking it for magic. The quantum revolution deserves more than awe, it demands clarity. Explaining quantum entanglement is like trying to describe color to someone who's never seen light. The concepts feel alien because they defy everything our senses tell us about how reality should work. But what if we could bridge that gap? Traditional teaching methods, blackboard equations, and abstract thought experiments often leave students more baffled than inspired. That's why educators are turning to radical new tools, like interactive quantum simulators that let learners play with entanglement firsthand. Picture a video game where you manipulate virtual particles, watching in real time as changing one instantly alters its partner across the screen. These simulations don't just illustrate quantum rules, they make them feel intuitive, transforming spooky action from a confusing paradox into something you can almost reach out and touch. Art, too, is becoming a surprising ally in demystifying the quantum world. Take the work of multimedia artists who translate entanglement into immersive installations. One project projects entangled photons' behavior onto a floor-to-ceiling canvas, where their correlated states paint swirling patterns of light. Step into the exhibit, and you're surrounded by the invisible dance of quantum connections, making the abstract visceral. Music composers have even sonified entanglement, assigning quantum states to musical notes. When one particle's spin flips, its partner's note changes in harmony, no matter how far apart the speakers are spaced. These approaches don't replace the math, they create an emotional hook, a moment of awe that makes students want to understand the equations behind the experience. The key lies in meeting learners where they are. For young children, that might mean replacing Schrödinger's cat with a quantum version of hot and cold, two boxes that always contain opposite temperatures, no matter how far you separate them. High school students might build simple interferometers with laser pointers and mirrors, observing how light behaves as both particle and wave. Even social media is joining the effort. TikTok creators use split-screen videos to demonstrate non-locality, with one person's actions instantly affecting another's feed miles away, a digital metaphor for entanglement's eerie synchronicity. But accessibility isn't just about tools, it's about language. Physicists are rewriting textbooks to ditch jargon in favor of vivid analogies. Instead of wave function collapse, students might hear about a crowd at a concert. Before the band is announced, the audience hums with possibilities superposition. But the moment the singer steps on stage, those possibilities snap into a single roaring cheer measurement. It's not a perfect analogy, but it grounds the unfamiliar in the familiar. Teachers are also borrowing from storytelling techniques, framing quantum phenomena as cosmic detective stories where entanglement is the hidden clue tying everything together. The stakes here are higher than just better grades. Quantum technologies, from medical imaging to climate modeling, will shape the next century, and we need a society that understands them. By making entanglement relatable, we're not just training future physicists, we're empowering everyone to engage with a world where the impossible is just another Tuesday. After all, the quantum revolution won't be powered by equations alone, it'll be driven by curiosity. And that starts with seeing the universe's weirdness not as a barrier, but as an invitation. When we think of quantum physics, names like Einstein, Bohr, and Schrödinger dominate the narrative. But behind the scenes, women have been quietly rewriting the rules of entanglement since the field's earliest days. Take Emmy Noether, a mathematician whose groundbreaking theorem in 1918 revealed an astonishing link between symmetry and conservation laws. While not a quantum physicist by title, her work laid the foundation for understanding why particles conserve properties like spin during entanglement. Noether's theorem proved that every symmetry in nature corresponds to a conserved quantity, a revelation that later physicists would use to decode the strange persistence of quantum correlations across space and time. Yet for decades, her contributions were sidelined, her lectures delivered under a male colleague's name because universities refused to hire women professors. The story repeats with Qin Xiong Wu, the First Lady of Physics, whose experiments in the 1950s shattered the notion that nature treats left and right equally. Her meticulous work on parity violation didn't just earn her male colleagues a Nobel Prize, it indirectly exposed the fragility of classical assumptions that had long constrained thinking about quantum connections. Wu's hands-on brilliance in the lab revealed that the universe has a handedness, a finding that subtly paved the way for later discoveries about how entangled particles share information non-locally. Despite her pivotal role, her name remains absent from most introductory physics textbooks. Fast forward to today, and women continue to push entanglement's boundaries, often without fanfare. Elena Riefel at NAS, a quantum artificial intelligence lab, pioneers algorithms for quantum computers that harness entanglement to solve optimization problems no classical machine could crack. Meanwhile, Antonella de Pasquale's theoretical work on quantum thermodynamics reveals how entangled systems might one day revolutionize energy storage, with particles coordinating their states to sidestep classical efficiency limits. And let's not forget Michelle Simmons, whose team in Australia builds quantum transistors atom by atom, turning entanglement from a laboratory curiosity into the backbone of future electronics. Yet the challenges persist. Studies show women in physics still face citation gaps, their papers referenced less often than male peers' work of equal quality. Early career researchers grapple with the leaky pipeline, where systemic biases drain diversity at every academic milestone. This isn't just a moral issue, it's a scientific one. Quantum physics thrives on diverse perspectives. Entanglement itself teaches us that systems are richer when connections are multifaceted. Overlooking women's contributions doesn't just erase history, it impoverishes the future of discovery. The lesson is clear. Advancing quantum science requires more than brilliant minds. It demands equitable recognition. From Noether's symmetry insights to today's quantum engineers, women have been the silent architects of entanglement's most profound revelations. Their stories aren't footnotes, they're the hidden equations scribbled in the margins of physics, waiting to be integrated into the main text. Because if quantum mechanics has taught us anything, it's that reality is deeply interconnected, and so is the path to understanding it. The race to harness quantum entanglement isn't just scientific, it's a high-stakes geopolitical chess match where nations are betting billions on what could be the defining technology of this century. Picture the Cold War space race, but instead of rockets and moon landings, the battlefield is laboratories manipulating particles smaller than atoms. China has made entanglement its national priority, launching the world's first quantum satellite in 2016 and building a 2,000-kilometer quantum-secured communication network between Beijing and Shanghai. Their recent quantum processor, Zhangji, reportedly solved a problem in 1 hour that would take classical supercomputers 8 years, a flex of technological muscle that sent shockwaves through intelligence agencies worldwide. Meanwhile, the United States has funneled over $1.2 billion into quantum research through its National Quantum Initiative, with tech giants like Google and IBM racing to scale up superconducting qubit systems. The Pentagon views quantum tech as critical infrastructure, pouring resources into entanglement-based navigation systems that could guide submarines without GPS and sensors capable of detecting stealth aircraft through gravitational anomalies. Europe isn't far behind. The EU's quantum flagship program has mobilized over €1 billion across 20 countries, with Germany spearheading quantum encryption projects to safeguard government communications. Even smaller players like Singapore and Israel are carving out niches in quantum sensing and cryptography, proving you don't need superpower budgets to compete in this revolution. The strategic value of entanglement becomes terrifyingly clear in military applications. Quantum radar could render current stealth technology obsolete by detecting aircraft not through radio waves, but by measuring disturbances in entangled photon networks. Submarines might one day navigate using quantum accelerometers so precise they can detect minute variations in Earth's gravitational field, eliminating their reliance on vulnerable satellite systems. And the darkest scenario, a working quantum computer capable of cracking RSA encryption, the bedrock of digital security, would give its owner the keys to every encrypted communication on the planet, from bank transactions to state secrets. Yet this isn't purely a zero-sum game. The quantum revolution also presents rare opportunities for international cooperation. Research consortia like the Quantum Economic Development Consortium bring together academia, industry, and governments to accelerate breakthroughs while mitigating risks. Some physicists argue entanglement itself could become a diplomatic tool. Quantum-secured communication channels might one day host arms control negotiations, with the laws of physics guaranteeing neither side can eavesdrop undetected. The same technology that threatens global security could ironically become its most trustworthy safeguard. What makes this race different from previous technological competitions is the sheer unpredictability of quantum breakthroughs. Unlike missile gaps or semiconductor shortages, quantum advantages could emerge suddenly from a single lab's discovery, rewriting global power balances overnight. The nation that cracks scalable quantum error correction or builds the first topological quantum computer won't just gain an edge, it might set the rules for the next era of civilization. And that's why universities from Toronto to Tokyo are scrambling to train the next generation of quantum engineers, because the real prize isn't just controlling entanglement, it's controlling the future. Entanglement doesn't just defy physics, it shatters the very foundations of how we perceive reality. For centuries, philosophers have clung to the idea of locality, the belief that objects are only influenced by their immediate surroundings. But when two entangled particles instantly mirror each other's states across galaxies, locality crumbles like a sandcastle at high tide. Imagine two dice rolling in separate universes, always landing on matching numbers without any signal passing between them. This isn't just a challenge to Einstein's relativity, it's a direct assault on our deepest assumptions about how cause and effect operate. If actions here can instantaneously ripple to the far reaches of space without any medium or mechanism, what does that say about the nature of connection itself? The implications stretch into metaphysics, where the very idea of separate objects starts to unravel. Classical realism, the belief that the world exists independently of observation, takes a gut punch when entangled particles refuse to have definite properties until measured. It's as if the universe is a vast, unfinished painting where the brushstrokes only solidify when someone looks. Some philosophers, like Karen Barad, argue that entanglement demands a new framework called agential realism, where objects don't pre-exist their interactions but emerge through them. In this view, the universe isn't a collection of isolated things but a dynamic web of relations, where even the act of measuring a particle isn't a passive observation but an act of participation, shaping reality as it unfolds. Then there's the crisis in causality. Traditional logic insists that causes must precede effects, but entanglement blurs this arrow of time. In experiments like the quantum delayed choice experiment, particles seem to decide their past behavior based on future measurements, as if time itself is a tapestry woven in both directions. This doesn't just baffle physicists, it sends shockwaves through epistemology, the study of how we know what we know. If reality is this malleable, how can we ever claim objective knowledge? The empiricist tradition, which roots truth in observable evidence, staggers under the weight of quantum weirdness. After all, when observation creates the very thing it measures, the line between discoverer and inventor vanishes. Ethics, too, gets dragged into the quantum fray. If entanglement reveals a universe fundamentally interconnected at its core, does that imply a moral interconnectedness as well? Indigenous philosophies have long posited that all life is woven into a single, reciprocal web, a view that quantum physics now eerily echoes. Could the golden rule, treat others as you wish to be treated, find validation in the mathematics of entanglement? Or does reducing spiritual concepts to quantum correlations risk oversimplifying both? The debate rages, but one thing's clear. Entanglement doesn't just challenge our instruments, it challenges our identities, forcing us to confront whether self and other are as illusory as the classical boundaries between particles. The most radical thinkers suggest entanglement might even redefine free will. If every particle state is tied to another's, are our choices truly our own, or are we puppets of a cosmic quantum network? Libertarians argue that quantum indeterminacy leaves room for genuine agency, while determinists counter that entanglement's correlations merely hide deeper, unseen laws. The irony is rich. A phenomenon discovered in sterile labs has become the battleground for humanity's oldest questions about fate and autonomy. What emerges from this chaos isn't just a new physics, but a new way of being. Entanglement forces us to live with ambiguity, to accept that reality might be a conversation rather than a script, a dance of probabilities rather than a clockwork mechanism. The philosophers who dare to wrestle with it, from Whitehead's process metaphysics to Bohm's implicate order, aren't just speculating, they're sketching the blueprint for a worldview that can hold the universe's strangeness without breaking. And that perhaps is entanglement's greatest gift, not answers but better questions. As we stand at the edge of the quantum frontier, one truth emerges with startling clarity. Entanglement isn't just a feature of the universe, it might be the very foundation upon which reality is built. Think of everything we've uncovered: particles communicating faster than light, black holes storing information in quantum threads, even the possibility that space-time itself is stitched together by these invisible connections. What began as a mathematical oddity in Einstein's equations has blossomed into a revolution, rewriting not just physics textbooks but our understanding of existence itself. Consider how far we've come since those early debates between Einstein and Bohr. What the former dismissed as spooky action has become the backbone of technologies that sound like magic quantum computers solving problems in minutes that would take classical machines millennia, unbreakable encryption secured by the laws of physics, even sensors so precise they can detect the gravitational whispers of hidden dimensions. The irony is delicious. The phenomenon that once threatened to topple our classical worldview is now the tool we're using to probe reality's deepest secrets. Yet for all our progress, the most thrilling chapters of this story remain unwritten. Imagine a future where entangled networks span the globe, creating a quantum internet that teleports information instantaneously. Picture hospitals where quantum sensors diagnose diseases at the molecular level, or factories where materials designed by quantum simulations revolutionize energy, medicine, and transportation. The potential isn't just technological, it's philosophical. If entanglement teaches us anything, it's that separateness may be an illusion, that at some fundamental level, everything is linked in a cosmic dance we're only beginning to hear the music of. This isn't the end of the journey, it's the prelude. Every experiment, every theory, every aha moment in labs around the world is adding brushstrokes to a canvas far grander than we ever imagined. The questions we're asking today about consciousness, about the birth of the universe, about the nature of time itself, might find their answers in the quantum connections we're just learning to see. So as we sign off, remember, the universe isn't just stranger than we think, it's stranger than we can think, and that's what makes this exploration so exhilarating. If you've enjoyed unraveling these mysteries with us, hit that like button, subscribe for more deep dives into the wonders of science, and drop a comment below. What aspect of entanglement blew your mind the most? Until next time, keep looking up and keep wondering. The cosmos still has plenty of secrets